Slides.
Full screen, right?
Yes.
Okay. Okay. Awesome. Let's get started. First of all, welcome to the STONNE tutorial. It's really for me a pleasure to be here introducing the tutorial on behalf of Francisco. Francisco is connected remotely because he had some problems with the flight, last minute cancellation. But fortunately, he's going to join us virtually, and he's going to present. Now I'm going to explain the different parts that are covered in this tutorial. But before that, just need to acknowledge the people that are in charge of making this tutorial possible. So first of all, Francisco, who is the postdoc researcher in the University of Murcia. He is actually was PhD student of Manuel Acacio and myself. And we are all from the University of Murcia in Spain. Then we have Ravish, that is sit down there. He's a PhD student of Tushar Krishna in Georgia Tech. And he's going to start another part in the presentation regarding to OMEGA tool. So regarding the different parts, as I'm going to, after the introduction, I'm going to start with the flexible accelerator part. And after that, circular simulation, and then a brief introduction to the STONNE simulator. Later, Francisco is going to join us virtually, and he's going to continue with the hands-on on STONNE and SST STONNE. After that, the OMEGA part, that is an extension of the STONNE simulator, will be presented by Ravish. And finally, Tushar Krishna is going to conclude and present the roadmap of development and conclude the meeting, conclude the tutorial. So let's see if this works. Okay, this works. Okay. In order to run the tutorial, so these are the instructions to type, the Docker and then git clone in order to, you can take a picture maybe, and later on you can do that meanwhile I'm explaining the first part. So because it requires 12 gigabytes of this space, so later on you can be ready. Okay, so now I'm going to start with the first part. The first part, what you are going to learn essentially is the motivation of why the different mapping strategies that are necessary to map a deep learning algorithm based on DNNs and also GNNs, but the GNNs, graph neural networks, will be later explained by Ravish in more detail. Here, I'm going to just expose the DNN part, focus on that particular topics. So what you are going to learn is about the challenge of mapping, efficient mapping, and also why do we need flexible DNN accelerators or deep learning accelerators, and why they must be flexible. So let's get started. First of all, everybody knows deep learning applications are everywhere, from object recognition, image processing, etc., etc. And these workloads need to be run in two different stages, although there are some mix of them. But in general, typically we have a first stage, which is the training process that happens in very large clusters composed of CPUs, GPUs, or TPUs, or other kind of accelerators. And then we have the inference process, where that happens once the models, the DNN models, have been trained, so they can be deployed to make predictions, right? Typically on edge devices. That's why there are multiple types of accelerators that are everywhere in order to conduct this in a very energy efficient way, and also considering the timing constraint, maybe for real-time execution. So the thing is that, why do we need DNN accelerators? Okay, first of all, we need to compute millions or billions even of parameters. For example, the number of weights that are in different state-of-the-art DNN models. So this involves that there is a need for lots of parallel compute. On the other hand, in order to fetch all this huge amount of data, for sure we need heavy data movement, but we have very constrained, especially at the edge in its devices, about memory data that is moved, that is fetched from DRAM, that is off-chip memory, to on-chip memory, because the cost in terms of energy is much more heavy as compared to the cost that is required in order to do operation, in which the operands are in the register file, for example. So here it's very, very important to reduce energy. The problem is that contemporary CPUs and GPUs, even though they are very, very advanced, they can run for the training process, you know, this training of the deep learning models. The first part is the CPUs are inefficient. We want to run a lot of computation, billions of computation in parallel. And on the other hand, the GPUs need to reduce the energy in order to, you know, make them more efficient, right? So that's why we need to take advantage of deep learning, specialized architecture for DNN workloads. And here we are taking, you know, the idea that 20 years ago, even more, are about the design of systolic arrays. Systolic arrays are basically spatial accelerators. Here, there are an example in which, for example, MIT, Google TPU, etc., developed this kind of structure, compute fabric, in which we have lots of values, lots of processing elements that are interconnected each other. And then we have, you know, chip, or we have a memory hierarchy, right, in which all of them access. So in order to solve the problem, okay, we need billions of computation. So the idea is that we are going to spread the computation across all these hundreds of values. And for the heavy data moment, how are we going to take that? So to tackle that. So if we reuse data that is temporarily stored in the processing elements, local storage, and if we are able in these historic arrays to fetch data for neighboring processing elements, we are going to save a lot of accesses to DRAM, to the chip memory that is very costly. Okay, so I mentioned that we need to exploit the data. We need to optimize and use as much as possible data reuse. If we look at the algorithm perspective of data reuse, here we can think about, okay, the types of typical DNN layers that happens in contemporary DNN workloads are, for example, convolutional layers. This is one example in which, if we think about how, you know, the weights in the filter are computing using this sliding window approach, essentially you can reuse multiple, you know, not only the filters that are, you know, happen in the sliding window, you can reuse them, but also there are certain parts of the activations or the input data that also can be reused. From another perspective of how are we going to leverage reuse at the from the algorithm point of view, so similarly for convolutional layers and fully connected layers, we have a set of filters, and then all of them are taking data operands from the same input F maps. So here we also have opportunities for reuse at the level of the activation. And finally, this is another example in which if we have large batch sizes, or if we have a batch size larger than 1, happens that, okay, we can again apply the same filters, the same set of filters to different input F maps. So here again, we can reuse at the level of filters. Well, this is from the algorithm point of view. We need to deeply understand how this can be actually taken into account in order to optimize, you know, the execution of DNN workloads. First, we need to understand what are, you know, the different, when you have a DNN workloads, essentially what you are using is a set of matrices, tensors in general, with different dimensions. We can see that like a 7-dimensional network layer in which weights input and then generate outputs need to be partitioned in an efficient way and mapped onto the hardware accelerator substrate. So we need to understand, in order to take advantage of reuse opportunities, how this mapping is conducted and what kind of data flows happens inside this mapping process. A data flow is essentially inside the accelerator, what are the data communication patterns between the memory components at the compute and the compute components. So this defines the data flow. In a very detailed definition is basically when you are conducting the mapping across all these dimensions, how are you going to order the computation? Because there will be some dimensions that are slower because they are in the outer loops and other than faster than in the inner loops. So the outer loops can be called stationary, while the others are like streaming, right? So this compute order defines also data flow. But in terms of, for example, optimizations about parallelization strategy, where you can unroll different loops in parallel, especially, so this is another opportunity that defines the data flow. And also the tiling strategy. Okay, we have tiles in order, because we basically need to keep on chip as many data as possible in order to avoid access to DRAM, right? So the tiling strategy also defines the data flow. So this implication need to be carefully understood in order to optimize the execution and the definition of the design of the accelerator. So in terms of hardware, what kind of hardware structure can be leveraged in order to implement this data reuse? Okay, data reuse, we have many different options. Here I show 3 of them. So first is about the temporary use. So look at here, we have different set of processing elements on this x-axis and the y-axis with at the time. So temporary use means that one processing element generates an output, and the same output need to be taken again in order to do another processing with it. How are we going from the hardware perspective to leverage it? So basically, to have a memory hierarchy. We have a memory hierarchy. We can take again, the data that has been stored in the first part in order to do in the first stage, in order to use it again in the second stage. For the spatial reuse, essentially, it means that you have data that need to be, multicast or need to be broadcast through two different processing elements to be computed in parallel, and then another set in the second time. So in order to implement this spatial reuse, what kind of hardware can we provide there? Of course, multicast support at the level of NOCs, or spatial temporal reuse. In this case, you have data that is produced by one processing element, and this data need to be fetched by another processing element. In order to enable this communication, we of course need to implement some kind of neighbor-to-neighbor connections. So these are the things that we need to leverage in order to design an accelerator for DNN processing. Okay, we have given just a brief overview about the requirements. Now I'm going to motivate the benefits of mapping flexibility. Okay, why do we need flexible DNN accelerators? So the first order is that, okay, there are myriad of diversity in terms of DNN models. We have a huge amount of applications that are emerging. We have a huge amount of models that happens, regularly, and they are even increasing. So essentially, we have many different layer types, layer sizes, and shapes. On the other hand, we also have diversity in the level of implementations. So what happens here is that you could have a convolution layer, but this convolution layer can be implemented in many different ways. So the wide, point-wise, or whatever. And also, we have opportunities that this hot topic nowadays is about how are we going to exploit sparsity. Sparsity happens when you are removing some neurons or some weights, some connections between neurons. That happens naturally when you have, this kind of activation functions such as ReLU, or you have weights that are 0 or close to 0, right? So this defines also that the accelerator need to be flexible in the sense that it need to be good for all conditions, for all these kind of situations. And finally, of course, the diversity in terms of mapping and data flow, depending on the data flow strategies that I commented earlier. And also partitioning strategy per layer or across layer. So there are many different possibilities. And here, for this all myriad of irregular shapes, sizes, etc., we need to be good, and it's the challenge. We need to get high utilization from all cases, in all scenarios. But wait a little bit. So, but it is DNN just a matter of GEMS operations, matrix multiplications? Yes, but there are some important aspects that we need to consider. Imagine that we have this GEM operation. Is typically assumed where we have, for example, it is defined in the tensor. Is defined in which we have two different matrices. We have matrix MK, matrix KN, matrix A, B, can be input, weights, etc., to produce an output. And then we have the accelerator substrate, for example, a TPU like this. We need to define first what is mapping efficiency. Mapping efficiency is basically the percentage of peace with useful computations. And the utilization is multiplying the mapping efficiency times the activity. Considering the mapping efficiency, we could have the situation where we have regular computation. Regular computation means that the matrices, all matrices A and B, fit completely and perfectly onto the accelerator substrate. So in this case, for example, if we map each individual rows for each individual columns, then we can compute, we can make a stationary the first matrix while we are streaming the other one, and then compute one element at a time using this historic array. We are achieving 100% mapping efficiency. This is for a regular case. But in order to support this, I'm going to explain later, but Essentially, we need here the row multicast and also column reduce in order to make this possible. Okay, that's perfect, that's good, but this is just an ideal case. In the regular case, in the common case, but this is not the regular case, in the common case, we would have irregular matrices in the sense that, okay, here we have matrices that are smaller than the dimensions that are of the accelerator array. So what happens here that you need 2 iterations in order to compute this matrix multiplication. Essentially, we can obtain 50% of mapping efficiency. And in the other case in which you cannot fit completely the matrices onto the accelerator for one of the dimensions, means that you cannot, since it is with 5 columns and you have here basically 4 process elements, you cannot map the 5 at the same time. So you need to iterate twice. And what happens in these 2 iterations, you are reducing the mapping efficiency a lot until, for example, in this case, 90%. So, and in terms of sparsity, you know that there are zeros in the matrices. What happens is that if we are mapping all of them as they appear in the without any compression scheme, you are mapping the zeros onto the processing elements. You are again having this degradation in terms of mapping efficiency. So we need mapping flexibility. That's the key. Mapping flexibility at the high level, in theory, is like, okay, you have here, you can accommodate more than 2. In order to avoid the 2 iterations, just map the first and the second one with the idle processing elements. And then you compute two outputs at the same time in parallel. Okay, that's, from the ideal point of view, the real perspective. In terms of irregular, when you have irregularity in which you cannot accommodate all the matrices for one of particular or 2 the dimensions or any dimensions, here 2 because we have this historic array, what you can do, okay, let's put those elements that kind of fit in the idle processing elements. This is when we are enable this ideal mapping flexibility. Or when we have the sparse computation, okay, let's map only the non-zero elements onto the processing elements in the systolic array. And then we are achieving very high, almost in this case, 100% mapping efficiency. So the key is how are we going to truly achieve this? So how we are going to support this in hardware? So here there are 2 different points that we need to consider. First is the distribution of data, input and weights, and then the reduction in order to do the collection, that is the final calculation of the dot products. We separate these 2 different things. And how are we going to support each of them? So these are the clues, these are the things that we need to provide. Here, we need to achieve these spatial multicasts or multiple power reductions in order to get to 2 different outputs at the same time, or multicast to neighbors in order to accommodate, this fifth element here in another process element with variable length, or send the non-zero elements, etc. So what kind of, and now there is another question is about what kind of level of flexibility we need to, or we should provide, we must provide. So in the first case, in order to understand what kind of flexibility here in this ideal scenario where we have this regular computation, let's first define what is a cluster. A cluster is a set of processing elements. Depending on the number of elements in this cluster, and depending on if you enable having different sizes for the clusters, we could have homogeneous clusters or heterogeneous clusters, while in the heterogeneous case, you have multiple sizes of clusters, so that we are providing the highest flexibility as possible. So let's give here an example, here, more detailed example. This is like a fixed homogeneous cluster where you have a fixed cluster size that depend also on fixed aspect ratio. So we have 4, 4, 4, and 4, and that's all. This is very good for regular computation. But when we have this situation that we need to reduce 2 at the same time, here we can have clusters of not the size of the accelerator size for one of the dimensions, but we could have limited choices here, cluster of 2, right? But not with a lot of, with all possibilities. The all possibilities comes when we have fully flexible homogeneous clusters, where we have here 5 times 3, now for this particular layer. Later we could have, I don't know, 6.2, but this is just fixed for a computation of a layer in a DNN workload, or a phase in a processing of a DNN workload. Or in the extreme case is fully flexible, but heterogeneous clusters, we would have clusters with different sizes at the same time. 3.1, 3 times 1, 2 times 1, 4 times 1, etc., etc. So we need to get these fully flexible heterogeneous clusters or something in between, right? So just to summarize the first part of the mapping challenge, there are irregular and sparse gems that introduce underutilization. And in order to get the desired features, in order to get 100% utilization, we need to focus on the distribution part of the computation and the collection part. For the distribution part, we need to get variable size multicast, multiple in parallel, and then sending just the non-zero for the sparse computation. And the collection, we need to reduce with variable size and multiple in parallel. Now, this is the first part, the first takeaway, mapping flexibility. And now, why do we need these flexible accelerators from the perspective of, okay, let's focus on the communication. Let's focus on designing communication-centric accelerators. So this is the typical systolic array, rigid array. This provides fixed homogeneous cluster, as I described earlier. But how are we going to provide part flexible, full flexible, heterogeneous, and homogeneous clusters? So what we need to do is to isolate what is the processing elements from the interconnect first. This is the first part of the design. And then we need to think about, we are going to have, since there are two different stages that are important, distribution and reduction or collection, let's first design the properties or see what is the implementation of the best distribution network to provide this flexibility. Okay, so by doing that, with respect to the distribution network, we see that, okay, we need to distribute the weights and inputs for all mapping possibilities. We can provide here many different types of topologies in order to implement that with different properties in terms of latency and bandwidth. Or we can even implement some optimizations in which we could have local forwarding between processing elements that communicate among them in order to exploit a special temporal data reuse, or we could have some multicasting support, efficient multicast support. These are desirable features. But what about the collection network or the reduction network? In this case, again, we need to collect final or partial output for multiple processing elements at the same time. We have many different options in terms of topology that we can implement here in order to provide the lowest latency and the highest bandwidth in order to do that, or implement some optimization in terms of in-network reduction, so that, for example, the TPU, what happens is that you are temporarily, you're especially accumulating, reducing the elements that are produced by a single column before the last processing element outputs release the final results. So there are many optimizations. And if we take a look at the different accelerators that have been published and others that are in the academia and industry, so we can see multiple options in terms of topologies for the distribution and reduction network and the level of flexibility that we can achieve. In this presentation, we are going to focus later in the Mary architecture and also the Sigma architecture. The first one can provide fully flexible homogeneous clusters, and the last one provide that, but also with the possibility of heterogeneity in terms of having multiple size clusters and support sparsity. These are, and also the TPU, these are the types of accelerators that are everywhere, that are nowadays has been proposed, and also STONNE, which is a simulator that Francisco is going to introduce later on, is able to model properly. So just go a little bit more with a deep dive into the why Sigma architecture is better with respect to the conventional systolic array or TPU. Let's consider this sample in which we have the two matrices. We are going to make stationary the values of this second matrix, while this will be streamed. And then this is the typical, stream fashion in which you run, the systolic array, this matrix multiplication on the systolic array. And we compare then this against the one that we could have in a Sigma architecture. This is the high level overview, where we have the distribution and reduction networks. And we have all we need to do the same operations. And we assume here 16 processing elements in order to have, a fair comparison. So the first step is to make stationary all the values. Here, we cannot do all of them. But here, thanks to the flexibility that enables the distribution network, we could map all that we can fit onto the accelerator. This is the first stage. The second stage is just multicast all the elements of the first row to the particular process elements that need to be, processing those elements. Here we are doing the same for the second row, the third row, the fourth row, and sigma is done. While in case of the systolic array, it takes a lot more cycles, almost twice, right, in order to do the same computation. So look here, the benefits of having flexibility, supporting in hardware. Later on, I'm going to present a little bit an overview of the architecture. Then, considering sparse computation for irregular, gems, let's do the same experiment, but in this case, again, sigma, again, with respect to the systolic array, we do the same operations, but here we are propagating just the non-zero elements when we are streaming the first matrix, so that we are done in sigma, but the systolic array takes almost 3 times clock number of cycles. This happens because sigma is able to just map non-zero stationary and then reduce the number of foldings, the number of iterations to do the process elements with respect to a systolic array. Now, I'm going to present briefly the case study of Mary and sigma, the high-level architecture, because this will be implemented in STONNE, and they're going to be presented later. So the Mary abstraction, this has been developed by TwoShark group. So the idea is that we need to compute the dot product operations. So we have multiplications, we have others, multiplication that happen just before the reductions with the others. So essentially we can view the Mary abstraction, which is basically a pool of multipliers and a pool of others, and then we have a global buffer or prefetch buffer on chip, where you are fetching the weights and inputs, and then you are output the data, and then you are computing all the dot products operations. So here we define, or Mary architecture defined the abstraction of having a virtual neuron. A virtual neuron is the one that is define a set of process elements, in this case, a set of multipliers, a set of others that are responsible for computing multiple dot product operations in parallel. So this has been introduced in the Mary abstraction and is leveraged by this and also by the Sigma architecture. The Mary implementation, if we look a little bit deeper, so we can see that, okay, we need to have the distribution network, and we have the reduction network, as I commented earlier. The distribution network here is a distribution tree with Chubby tree, that is, we have fat links in order to provide the highest, bandwidth for doing multicast, for doing the spatial reduce. Then we store the data locally in order to exploit what is the temporary reduce before the multipliers. And then the multipliers, we also enable here with the Mary architecture, the forwarding links, so we can exploit the spatial temporary reduce that happens naturally in convolutional layers. And finally, we have the reduction network. In the reduction network here, it is proposed an augmented reduction tree, an ART, which we have links. It's like a tree, a Chubby tree, with links between sibling and others in order to support multiple reductions in parallel and in order to provide the desired flexibility. So we have all of these, special reuse, special temporary use, all at the same time. And what is the, the secret sauce in order to enable that is basically the implementation of micro switches. Micro switches are everywhere. Here at the level of the distribution suite, the distribution network, each of the nodes is basically a distribution switch that provides flexibility in terms of how you're going to distribute the elements, left, right, or both at the same time in order to multicasting. Or we could have these multipliers that essentially comes with tiny switches in order to forward or do the multiplications. Or here in the reductions is like 3 times 2 other switch, which we would reduce data from different elements with the 3 inputs that we have different possibilities. So the key idea here is to program this Mary architecture, the memory, the control logic of the Mary architecture need to be programmed by a mapper, by a compiler, right, in order to provide all the possibilities. Okay, just in terms of summary of Mary features, okay, it's a communication-centric approach to design DNN accelerators. This is key because this is just what we leverage in order to design a STONNE simulator, because it implements these different networks as I will describe just after this presentation. So the Mary has these special features in which it distinguishes between different distribution, reduction, and multiply networks that enable all these multicast and all the reductions in order to support all kinds of data reuse. And then we need these micro switches, like with micro switches, in order to reconfigure the architecture for each individual workload to make it efficient, the execution. Okay, finally, just very briefly, Sigma extends the idea, the design philosophy of Maori architecture, where we have distribution network. There are multiple options. Some of them are more efficient than others. For example, we could implement unicast and multicast by using crossbar or a PINIS topology. These are the topologies that are here. Finally, Sigma implements a BINIS because it's more scalable. And with respect finally to the reduction network, we have here the topology. This is called the forwarding other network of FAN. Essentially, this is again as similarly to Maori architecture is like a reduction tree. But what happens here is that the others are simpler, are just two input others, and we have multiple connections, the forwarding links to different levels. So we support, the flexibility required in order to implement multiple and concurrent dot product operations with virtual neurons at the same time in a non-blocking fashion. So just to conclude this first part, first, DNN models are evolving rapidly. We need flexible mapping. In order to design the next generation DNN accelerator, we need a philosophy inspired into the communication-centric approach in which we distinguish between distribution, multiply, and also reduction network. And we need to, in order to provide the flexibility, we need to implement this lightweight, the lightweight tiny switches that are inside the network topologies, so that we can create dot products of arbitrary sizes. And I have presented my Sigma in order to motivate, these successful DNN accelerators that implement this. Okay, so this is the first part, the final of the first part. Any questions so far?
How does memory play a role in this? You can choose different aspects of memory when you're designing these architectures.
Yes, memory controllers are essential in this kind of architecture. In fact, in a STONNE simulator, we have, we have adopted the general case in which we could have sparse memory controllers that also take into account sparse compressed data formats. For example, you have, CSC, CSR, etc. This is implemented at the level of the memory controller, or either we could have dense memory computation. And I will explain later on how this can be managed using the STONNE simulator. But this is key, absolutely.
And one other question I had was what if there are temporal states or displays that you want to store during an operation? Now in German, if you have different actions that you want to store. So how do you communicate between these data points in the grid?
Yeah. So what happens is that typically, since an accelerator can accommodate, matrices with thousands of, elements per dimension, we need to partition those matrices in tiles. So once you send a tile to the accelerator, it computes all the operations. Then the output is stored in the global buffer of memory. If it cannot fit, you need to go to DRAM. But we need to be aware about these memory controllers in such a way that you can smoothly transition between the different tiles, so that you are optimizing at the end of the day what is the data locality inside the accelerator as much as possible. But this is just many different, optimizations that we could apply there. And we have considered, in order to implement, for example, the Sigma, we have been inspired by the mRNA, which is a mapper that has been developed in order to define the tiles in an optimized way, in order to leverage this temporal locality that you need to exploit between different tiles. Okay. Go ahead.
In your simulator, if I want to use some other different compression mechanism,
yes,
rather than CSR or something like that,
yes,
is it possible to model that kind of things to your simulator?
Yeah, absolutely. In fact, we have incorporated into a STONNE simulator, we have bitmap, we have CSC, we have CSR, and other could come, we need to implement that, but the extension can be, done perfectly from the perspective of the memory controllers. So later on, I'm going to explain how the memory controllers are essential in order to provide the flexibility.
And do you have any relationship between the compression mechanism with your operation key or information network architecture? Is there any relationship between the performance of something?
Yeah, depending on the type of compression format, you could have, worse or better performance. The thing is that this is a lossless, computation. Is lossless compression in the sense that you are the operands in order to do the dot product are the same. So the metadata is what matters, that defines, bitmap or CSR or CSC, that also affects the memory footprint that you would have at the end. These are choices that can be exploited by leveraging the STONNE simulator, because we have different options and also the possibility to incorporate even more in order to do these trade-offs. Any other question? Yeah.
So, from what I understand, the basic philosophy here is instead of using structured data flow accelerator, you have a flexible data flow accelerator, which means you basically move the burden of optimization to the distribution and reduction network rather than to the architecture design. Is that right?
The architecture design is prepared in such a way that you can configure the data flows that you will have mapped. So in order to do that, you need to program, but not the programmers, but the compiler or the mapper that maps the computation to the hardware need to program these tiny switches that are at the level of the interconnect. That's why this is communication-centric design of the accelerators.
So it's almost knock-like stuff.
Yeah, exactly.
And so what is the extra overhead we're getting? So what is the extra stuff we have to put in the chips? What about the chip size? The power usage, all of that.
Yes. In the paper of Maeri and Sigma and also other that also is not here the reference. At least I'm not the owner or co-author of Maeri and Sigma, but I mean the group of Tushar Krishna is. They measure, what is with respect to a TPU that is regular fabric, which is the overhead that you have in respect to area and power. But the thing is that in terms of performance per watt, Maeri and Sigma is much better. There is an overhead for sure because you need to introduce these switches, but they are lightweight switches, so the overhead is not very bad, and the architecture is scalable as well. Sigma, for example, has considered also to develop a clusterized version in order to do training, because Maeri is for inference of DNNs, right? Sigma is for inference, but also they have the possibility of a scale out and a scale up in such a way that is also scalable enough for training. And compare, against GPUs, they are vast and they are more energy efficient. What we need to provide at the end of the day.
And the throughput.
The throughput is even better because they are specialized accelerators just for these particular DNN goal loads, while, for example, GPUs are more general purpose. So that means that you need to introduce there more hardware in order to accommodate all types of workloads.
What I meant by throughput, because of is the throughput affected due to the introduction of the distribution and the reduction?
Memory throughput?
Yes.
Yeah, absolutely. For that reason, we need to take advantage of advanced memory technologies such as HBM2, for example, in order to provide enough memory bandwidth. So even though you are data reuse a lot, much better with respect to a GPU, but at the end of the day, you need to fetch billions of weights, right? And if you need to do that in real time, so you need to have these advanced memory technologies.
So I think also I would like to add. So
yeah, absolutely.
Compared to the other thing that that works in the advantage of Maeri and Sigma is that you have 100% utilization of the piece. So the overall output, overall throughput, overall outputs that you are getting per second increases because it is making full use of the architecture compared to let's say a static array on which you can't fully map the workpiece.
Okay, and the latency is not so throughput, of course, like you said, 100% mapping efficiency, so you get a lot of throughput. My question was more like the latency introduced by the networking.
So Maeri is basically pipeline. So one of the stages is the complete distribution network, and then multiplier network is one stage of a pipeline. So there are feed 5% between which basically enables pipeline operation. And then at each stage of the reduction network, there are fibers which enable pipeline. So the latency of an individual stage is not affected civilians.
Yeah. Yeah, and the network also, in terms of distribution, we by providing this kind of network, we are achieving O1. There's no complexity of latency and also reduction in log n because you are reducing in a tree. So it's much faster with respect to a GPU, for example, with the whole memory hierarchy I need to go. Okay. Any other questions?
Is there any configuration overhead for the network?
Sorry?
Configuration.
The configuration for the network. Yeah. But in the simulator, of course, you can configure that is the number of process elements, the compute capability, the operand size, that is the type, if they are 16 bits, the operand source 32 bits or 8 bits. I mean, you have the possibilities.
Yeah, but I'm asking that some kind of overhead for the configuration.
The configuration happens just dependent on the data flow, but you can run it just at the beginning of a layer. We are mapping that is layer by layer. So one particular layer you configure first, and then you run it. And then you configure the second layer, or you can leverage the configuration of the first layer to run the second one. So since the layers are typically very large, so you are amortizing all of this configuration step. Okay. Any other question? Okay, so let's move on to the second part of the tutorial. Now, what is the time? Sorry. So
230.
2:30. Oh, I'm a little bit over. I'm going to summarize this part and then I'm going to give the word to Francisco.
I have a question.
Yeah.
Will you post this slide? And,
Yeah, we are going to post and we are recording it. So give you just a brief introduction to the STONNE simulator. And here, the first thing is, why do we need cycle level architectural simulation? So this has been done. I'm going to summarize a little bit at the beginning. Cycle level architectural simulation happens when we are observing, the developments in CPUs, in GPUs, right? We have GEMs, Gen 5, we have NGPU scene, Navi scene, we have GPGPU scene for GPUs, etc. Now it's the question, okay, do we have this cycle level simulation at the level of DNN architectures? So this is very powerful cycle level architectural simulation, because if we want to tape out a chip, what happens without architectural simulation, cycle level architectural simulation, is that, okay, you implement your architectural design ideas, you implement RTL with synopsis, cadence, tools, etc. You verify at that level, and then you manufacture. This is not ideal. There are multiple iterations. And if we don't consider architectural simulation, this happens, and there are a lot of errors, it's error prone, etc. Maybe you won't have, you think about an idea, but then when you are implementing that after 3 or 4 months of hard work, then you realize that this doesn't make smart sense. So using architectural simulation, but at the cycle level, which is very precise simulation, you build a simulator in C++, for example, high-level language, then you test the simulator in software, testing techniques. And then once you are convinced that this kind of architectural innovation is good, then you go through the conventional stage. This happens for CPU simulator, GPU simulators, but it doesn't happen so much or that much when we consider DNN accelerators. In terms of DNN acceleration, that's why we have proposed STONNE as a simulation tool for neural network engines that, as we demonstrate in this tutorial, it is a valid tool, a very valuable tool for DNN architectures, but also we extend it properly, as in the Omega part that Ravis is going to explain. It also is good. It's very good, appropriate tool for GNN workloads, graph neural networks workloads. So STONNE essentially at the very high level is like this. You have a configuration file describing the architectural features of the simulated or the model DNN architecture. Then we connect STONNE as a backend of a framework that is very popular, such as Pytorch or even Café, that we have another version, that you have, the definition of a DNN model, and the Pytorch with the different types of functionality calls STONNE as another accelerator device, so that you get, the execution of a DNN model. Here, what happens is that STONNE is able to report statistics of simulation as any other simulator. also reports energy area consumption. This happens, in general, because for every particular DNN workloads, you can change, the configuration parameters of the accelerator model, and it reports what is, the area overhead. But in terms of energy, it can report static energy, dynamic energy as well when you consider the particular DNN workload that is the DNN model that you are running. And for sure, it can output, the prediction as another accelerator backend of a particular DNN model. Okay, this is a dog with this percentage. So what do we need? The style is changed a little bit, but I think that is fine. So why do we need another simulator for DNN accelerator? So essentially here, this is the paper where we published STONNE for the first time in this conference. And we have, in that paper, we have a table that essentially compare all the different contemporary simulators for DNNs. And we appreciate different categories depending on whether the simulators are cycle level or not, the type of accelerators they can model, flexible or rigid, that I explained in the previous part of the presentation of the tutorial, if they support sparsity in the execution, if they can execute full models, that if you have a unmodified or a DNN model with 1,000 on layers, then you can fetch one by one and accelerate and execute that, simulate that. So surprisingly, there are simulators that don't allow this. And data-dependent optimizations, I'm not going to cover this because will take more time, but just to give you a brief idea, there are some optimizations that can be only possible when you are reading and viewing the value of the parameters that you are computing. In dot products, for example, you could have a 0, right? You could have 0 times 2, right? It is 0 always. So the 0 matters a lot. But in this special case, it is simple to see. But in others, you could also have optimizations in which you reorder the weight values in such a way that, for example, you'd make dot products operations. In convolutional layers, convolutional networks, you have typically a ReLU activation function. So all the values that are under 0, that are negative, they become 0. So if you reorder the weights in such a way that you make sure that after a certain number of computations, you are getting 0, and beyond that, because of the ordering of the weights, you are still going to be 0, negative values. So just cut off, the computation at that moment and avoid further computations, because at the end of the day, the results will be negative. So these are optimization at the level of data-dependent optimizations, and STONNE is the only simulator that is able to do that. So we compare here against the RTL models that are prototypes of MRSIM architecture. They are the most precise, prototypes in order to simulate, in order to run the DNN models with these two simulators, but they are very constrained because they are the level of RTL. We also consider the idea of analytical modeling, in which we have analytical models. This means that, okay, something that we can do is that at the end of the day, DNN models, DNN workloads are dot products, GEMS operations. We could state different formulas that could represent, the DNN architecture in such a way that we can make a lot of easy, the understanding of the implications of a particular DNN workload in compute, right? This could be possible in terms of a TPU, for example. But when the models are more complex, or the complexity of the architecture is even larger, this is not possible. Or when you want to understand stalls in the compute pipeline, that happens, for example, when you cannot read an element. So analytical models that are not useful. They are useful if you want to provide some Pareto optimal parameter configuration for the accelerators, but when you deep dive, so we observe that analytical models lag far behind what is a cycle accurate, what is a precise runtime, modeling of the DNN workload. So this is what we here try to motivate, that is the comparison against a cycle level simulator against analytical model. And here, just to summarize, is we consider dense computation, regular computation, analytical models are very good, because you can see the bars that in similar colors, blues or reds or greens, they are matched more or less. But when you consider scenarios in which there are pipeline stalls, when you cannot guarantee that all the elements that are required, for example, for conducting the dot products are not fetched at the same time in parallel because you don't have full bandwidth from the global memory, from on-chip memory. Then you are observing that there is pipeline stalls, so the runtime is higher. So as we can see here, the STONNE with STONNE simulator, due to this cycle accuracy, it can report the stall time, so it can report higher times as compared to the ones that are of the analytical models that cannot model stalls at all. So you want to capture, the subtleties of the execution of a particular DNN workload according to the hardware. So analytical models doesn't work well, and doesn't work well at all when also considering a sparsity situation where not only the percentage of zeros in matrices are important, but also the distributions of those zeros that configure the virtual neurons that can be accommodated in parallel in a particular, DNN architecture. So here they are not very good at properly modeling the runtime. Cycle level simulation is key. So this part, I'm going to just briefly explain that there are 3 different parts in STONNE. It is implemented in C++. There is also code in Python, and also there are scripts in order to report, statistics, etc. But at the very high level, we have 3 different modules. The simulation platform that simulates the mapper, that the STONNE API and the mapper that are required in order to run a particular workload. Imagine a tile that needs to be run, or a layer of a DNN that needs to be run and simulated in the, for example, in a MAERI or a TPU-like architecture. So the TPU-like architecture of MAERI will be modeled here in the simulation engine, and here these are the mapper that are required in order to program, the configuration of the TPU or the MAERI architecture, and then simulate the layer. We have the input module. Basically, we have 2 possibilities in order to input the simulator. One is the Pytorch, as I mentioned earlier, with minor modifications. We are able to run full models. And we have also the possibility to have this STONNE user interface that basically is a command line in which a prompt in which you can program, you can set, specific configurations in order to run a particular layer that, you need to understand if one particular optimization is good or not. Don't just invest a lot of time just running the whole model or using the Pytorch framework that introduces, a lot of, it's difficult to be focused, right? Just focus on the particular layer that you want to optimize. And then that's why we provide also the STONNE user interface. And finally, the output module in which we report everything, all the data related to simulation, or the simulation output, performance, inference results, energy, and area. So this is the prompt with the command line in order to, simulate in the input module the STONNE user interface. So in order to program, at the level of the Pytorch, we would have, this is Pytorch in order to define a particular DNN model with different layers. And we have convolution, max pooling, etc. This can be programmed like this. For sure, if you run this in a CPU, all the layers will be run on the CPU. But we have just with very minor modifications to the names of the type of layers, we just add the word simulated. We add also the configuration of the hardware MAERI architecture, for example, that we will to launch this particular layer, so that when we implement the forward propagation, we just can, offload the computation to STONNE in the layers that have been programmed here. And the interface is very, very simple as Pytorch. Yeah, question. Yeah, go ahead.
Do you also support custom frameworks outside of Pytorch? Like if we have an accelerator that we don't use Pytorch to write our own language for it, or we have
we have
into the API.
Yeah, absolutely. We have a good experience because we started with Caffe and then we moved to PyTorch. But as long as we respect, the API, STONNE API that are very common, because it's essentially in the STONNE API we are defining. No, this comes later. We are defining, general types of layers. This API that we could essentially, run an operation, this run a layer, configure data that is for the memory, date weights where they are going to be put for the memory controllers, understanding. Or I'm going to configure a linear layer or a convolution layer, etc. So this can be easily adapted for a particular front end.
So So the user, so as an accelerator designer, I need to use this to.
Yes, yes,
So, just to add, there's
Yes.
a command line interface as well, so you can just run the binary with specifying the workload parameters and whatever like bandwidth you want to use and how you want to map the workload. So, yeah, you can do that. So right now there are some functionalities you can configure the parallelism sizes, but in order to like, configure the loop order and all, it requires some modification. But yeah, there is like a lot you can also do from the command line interface. Also, I think the API can be. Also, I think there is a way to connect it to like other simulators. Also, for example, you can hook it to a memory hierarchy from some other simulator.
yeah. This is the second hands-on that Francisco is going to explain. No, it's very good questions. So it's because we achieved to integrate a STONNE simulator with another one that help us in order to for the memory hierarchy modeling in a more better way. So yeah, so just to give you a little bit more context here, and then I'm going to give the word to Francisco. So the simulation engine is inspired by the architecture of a memory proposal in which the observation is that we can logically understand the architecture of accelerator, such as having three major neural networks on chip, some networks. So we would have the distribution network, we have the multiplying network, and the reduction network, as I explained in the first part of the tutorial. This can be this is very important because by analyzing this, if we put together multipliers and others, we will have processing elements that physically logically, while they can be understood as separate units, they are physically in the same processing element, or in terms of memory or sigma, they are separated at all from the logical perspective or the physical perspective. This design philosophy helped us in order to configure multiple types of reduction networks, multiple types of distribution networks, multiplying networks, the memory controllers that we were discussing earlier regarding if you implement dense controllers or sparse controllers here, we could implement the CSR, CSC, bitmap, etc., as an extension in order to incorporate these compression formats. And then we could, by smart combination of these components, by plugging them, plug and plug them, so we can see that we can configure memory, sigma, TPU, and also SNAPIA, which is another one that we also present here as a use case, etc. So in terms of validation, with respect to RTL implementation of this accelerator, memory, sigma, and TPU, we just guessed a negligible 1.5% on average deviation with respect to the cycles reported by RTL with respect to STONNE for a certain set of matrix multiplications. And then here in this paper, we presented 3 different use cases. One is the first one is comparison of the TPU, memory, and sigma accelerators and in terms of how they behave in terms of runtime and energy consumption. Another one is respect to how to implement data-dependent optimizations. The idea, so this is the first one, the comparison against the different TPU, memory, and sigma in terms of number of clock cycles and also energy. That is not presented here. The second use case, okay, now we are going to modify the backend of STONNE. We are going to provide another simulator, another accelerator. The other accelerator is SNAPIA. SNAPIA take advantage of this philosophy of, okay, if we reorder, this is the dot product operation, these are inputs, these are the weights. If we reorder the weights in such a way that while we are computing the operands, we see that the value is 0 or negative, we can cut off the computation without further processing more computation. It is very simple, as we can see here. 1 times 1 is 1, plus 4 times 2 is 8, 9, right? Overall, as a partial sum. And then we have 2 times -5, which is -10, -10 plus 9 is -1. Then, no matter the value that comes later, this will be negative. So we can avoid essentially 3 times -10. So we can cut off computation, we can save energy. Okay, So this is the idea that implement this paper, this architecture. This is another simulator. And then we incorporate also in STONNE this accelerator by adding a certain, at the level of the process element, negative detection logic. Then we reorder the weights, order the weights here at the level of for the front end, that is the Pytorch. We compare against, the layers that are in the paper of the SNAPEA, and we observe, very similar trends. So this validates, the implementation of this simulator, this new accelerator into the STONNE. And finally, just to conclude, okay, the complexity of DNN accelerators is growing a lot. We need cycle level simulation. STONNE is the right tool. One is as compared to the state of the art, is the only tool that is capable of providing this. And it can implement rigid, also reads as a TPU, flexible data-driven accelerator, performing actual computation, and also GNN workloads that you could, implement based on using STONNE, as we are going to explain later on. And thank you very much. Any questions? Yes, go ahead.
Sure. Does it also support reduce like mixed precision?
We have not incorporated yet mixed precision, but we can do that, absolutely. Just modifying, with the wires, we got different wires at the level of the network, and also the functional units, the other and multipliers. We need to provide both, but this is simple because this is cycle level simulation at the high level in C++, so we can integrate that. In fact, this was something that we were also trying to incorporate in another, paper that we are, starting to, think about for providing higher energy efficiency when you are computing irregular, DNN models.
Oh, sorry, you're using mixed precision. I meant to simulate mixed precision arithmetic, not use
Mixed precision arithmetic, exactly.
Not mixed precision arithmetic for simulation.
No. Mixed precision arithmetic. Yeah, exactly. So, any other question? Yes.
From a practical point of view, when I'm using this, is there a way for me to understand the mapping flexibility? Like, do I just provide a bunch of parameters and will I be able to see the mapping that happens to hardware? And like your visualizations were really good. So something like that, which is more intuitive as like output to post of analysis would be.
So there are two options. First is that you have, here we provide in a JSON file a summary of the activity for each individual, component that has been simulated. But also we have this specific set of counters that is another file where you could see the activity of all the particular elements, but one by one. This wire, what is the activity, right? This is just, you can fetch this in a script, and then you can understand, the statistics, providing plots, graphs, etc. Also, we had some experience in the past just trying to have for example, similarly to what we can find at the level of GPGPUs in simulator, where you could draw essentially the activity of a multitude scene. You could draw the activity. You could see wires that are in different colors. You would have, different mapping colors. Yes, map colors, and then you get red. There's more activity. We have some in the past with Maya architecture. This has not been released because we have been focusing on other things. But as part of a bachelor degree thesis, we had a tool that paints, the Maya architecture in such a way that you can see the activity. But that's.
So you mentioned the full, it can do full model.
Yes.
It can simulate the full model.
Yes.
Of the data types. So if the accelerator like pipelines computation between the different layers,
Yes.
is it able to handle that as well? Because I know time would be able to do one thing without.
Yes. Yes.
So,
the current implementation is just simulating layer by layer. There are intra-layer, optimizations that you could implement. For sure, this could be also incorporated into the STONNE simulator, but the current version doesn't incorporate this. We are preferring doing that now. Later on, we can extend it. In the roadmap of development, I don't remember if it is in the roadmap, but it's something that we have discussed previously internally.
So just to add, so later on I'll be presenting Omega. So what it does right now is So Omega models graph neural networks, which involves pipelining between two layers. So what it does is it collects timestamps of individual layers, and then it has an analytical model that can manipulate those timestamps to return like the simulated values.
Okay, like so it simulates the analytically.
Yeah. So the individual layers are still simulated, but an analytical model. So there is the timestamps are being collected, and then the analytical model can manipulate those timestamps and then see whichever is the slower one, and then it can add the maximum of. So yeah.
What's the speed of the simulation?
So we I don't remember exactly the the number of it depends heavily on the what type of layer you are going to simulate. But our experiences for certain models is like BERT, which I remember, I think that is the largest one. It takes us like 1-2 days to simulate the whole DNN, if I'm not wrong, more or less. But for sure, it depends. That's why we provide, the STONNE API, sorry, the STONNE user interface, where you can focus just in a particular layer with these particular, aspects. So later on, you can run the whole model. You can, run it in a cluster, for these are simulators, right? So it's something that we need to accept. Okay, we can discuss more later. So let's now continue with Francisco, who is going to Ravis. Please, can you help me? This is not.
Yes, I can.
For questions, right? So should we keep the mic on for questions from here?
Yeah.
I'll just stop sharing. Yeah, Francisco, can you try sharing your screen?
Yes. Can you see my screen now?
Yes, we can. I'll switch. Yeah, okay.
Thank you very much. Later on, we can discuss much more.
Okay, can you hear me?
Yeah. Yes.
Okay, let me double check it works. 1 second, it's working very slow. Okay. Okay. Works now. Okay, so thank you everyone for attending. Hello everyone. And first of all, so I'm really sorry for not being there. I should have been, but there was a problem with the flights, as Jose Luis said. So finally, I have to do this remotely. But okay, I'm happy to be here though. So yeah, this is the part where I will introduce STONNE by using some real use cases. Right. So first of all, I actually wanted to explicitly thank everyone, every organizer here, and even more now under these circumstances. Right. So mostly I would like to thank you, to thank Jose Luis and Ravis for organizing this on behalf of me. And also here I would like to thank Adrian Fenolar Navarro, right, who actually is not officially an organizer, but he has helped me a lot setting up this environment for these use cases, and he helped me a lot with the with some stuff regarding the configuration, and he's actually now taking over Stone, and he will be the maintainer as well together with me. So yeah, let's just get started. So first of all, I will try to cover a little bit about the installation of Stone very quick, and then I will go through to hands-on. In the first hands-on, I will be simulating a real DNN using Mary actually with Stone, of course. And in the second hands-on, I will show you, and this is new, because in the last year we also ran this tutorial, but this second hands-on is completely new, and here we are. I will be showing you how to run a new version of Stone, which is called SST Stone, and incorporates a new memory hierarchy. Okay, so let's start. Stone, as Jose Luis has mentioned, is available under the MIT license on GitHub, so everyone can go there and just clone the repository. It will be available, and it should be ready to run. It has some dependencies. You can see all of them here. I'm not gonna go through them actually. And so Stone can be actually very easily installed. You just have to clone the repo, type make in your terminal. It will be completely compiled and ready to go. Also, as Jose Luis has mentioned, Stone has a connection with Pytorch, right? So to install that, you just need to do this command python setup.py install, and then everything should work. Otherwise, actually, there is a full guide. There are full guidelines about how to install the simulator in the repository, right, on GitHub. So the good thing, the best of everything is that in order to avoid this, in order to avoid some headaches regarding the installation of Stone, we have set up a Docker image, which can be just downloaded and used by running this command that you can see here, sudo docker run, and then this is the Docker image that you can fetch and run. Once you are inside the Docker, everything will be set up there. STONNE, OMEGA, and SST Stone. Everything will be installed. You can use it. You can simulate any layer, any DNN, anything. And for this tutorial, we have prepared this new command, which is a git clone Stone simulator tutorials. This basically fetch the material for today's tutorial, the material that I will be using right now, actually. So let me start. So we are gonna fetch the image. I have already it in my machine. So once I run this, it automatically enters into the Docker. And the Docker has essentially three main folders. One is Omega, another one is Stone, and the third one is the new SST Stone. As I said, everything is installed, and you just have to follow the steps of this tutorial to set everything up and run any simulation. Okay, so once we are here, let's clone everything related to today's tutorial, right? So let's type git clone. Let me actually, I don't want to close this, so I will type it really fast. I want to exit because my laptop is running very small, I'm afraid. Simulator dash tutorials. Okay, sorry about that. Okay, so it takes very short, few seconds. Then once you are done, you have a new folder here, tutorials, and then on ASPLOS 23 is all the material that we would use during today's session. Okay, so let's continue. Yeah. So once we have the setup, I will explain a little bit the organization of the project. So again, we have a Stone, right? Stone folder. And then within Stone, we have another Stone folder, which is the one that contains the simulator. Inside this, actually, let me show it on live. Let me go back to the root, okay? And then we go to Stone. So here you see benchmarks, figures, blah, blah, blah. And then you have Stone, which is the simulator itself. We go to Stone. Let me hide this. And then here, this is the simulators folder. Here you have the Stone executable here, that you can use. This is the STONNE user interface that we will use. You can compile it using make. Everything is already compiled in the Docker, so you have to do nothing about it. And so let me continue. Yeah, you have here the Omega as well, right? Let me go back. Yeah, Ravish will take care of this. And also within STONNE, within STONNE, yeah, we have the executable, right? We have the includes, right? If you go to include, here are all the headers of the simulator for every reduction network, every distribution network that is here, multiplier network, every component of the accelerator is here, right? We have also, actually, let me follow the slides. And then, as you know, as Jose Luis has mentioned, just as a reminder, STONNE is organized like this, right? So we have um, three networks, right? The distribution network, the multiplier network, and the reduction network. And uh, the reason why STONNE is powerful is that it's able to simulate different reduction networks, different multiplier networks, different distribution networks, and these and different controllers as well. And this means basically that I mean the in order this to happen, we need basically to use abstract classes, right? So inside the headers, we have four abstract classes: reduction network.h, distribution network.h, and multiplayer network and memory controller, that basically abstracts the main functions of every uh, component that is supposed to be in the simulator, right? Also, for every abstract class, for every module, right? We have the um, the real networks, right? So we have, for example, AS network. We have the DS network, which is a tree. We have the multiply network for the TPU, the multiply network for Mary and Sigma. We have different memory controllers. One is dense, another one is sparse, another one is for the TPU or SMS, ST memory, and also other useful components like the data packages, which is the class that is used to create packets and which flow through the simulator, FIFOs or wires, which is connection.h, and also yeah, the STONNE model.h, which drives the simulator. Okay, so how does STONNE work? So basically, every component in the simulator, every multiplier, every multiplier network, every module in the hardware implements the void cycle method, which basically defines what that component does. So just a very quick overview. For example, here, if we go to the headers again, and we open the multiplier switch, which is the multiplier that performs the multiplications in the simulator, there is a cycle function here. Let me search. Voids cycle. Okay, right. And this function implements everything in the source file. Let me. Okay. Void cycle. No, sorry. Cycle. Yeah. So here, for example, is the implementation of the multiplier switch. Right. Everything that the multiplier switch should do in a particular cycle. Of course, I'm not going to get into details. I just want to give you an overview of how the simulator works. Okay, so what else? As I have said, SRC folder contains the main folder. There is one source for every header. Basically, every component of the simulator is a .cpp here, and there is this STONNE model.cpp, which is the one that drives the simulation. And how it works, this file has several like phases. We can say the first phase just reads the input file, right? Here is like the snapshot of the code a little bit. So it's this code basically selects the different architecture that we want to simulate based on the input configuration file, and it reads all the simulator parameters, right? Then after this, the class defines methods to load the layer, the tile parameters, the memory addresses, and basically it runs the simulation, right? And to do so, basically the simulator uses these functions: load DNN layer, load com layer, load full connected layer. So the STONNE model.cpp uses these functions to load a layer, to load a tile, to load a different matrix, etc., to configure the environment before running the real simulation. And the good thing is that by doing this, by creating this interface, anyone can actually take advantage of this structure and interface with the simulator. So you can create your own, I don't know, main.cpp file, include the stone model.h, and use these functions to load a DNN layer into the simulator, load parameters into the simulator, and run the simulator within your code without having to use the current Stone's interface. Right. So lastly, but not last but not least, the code, the stone model.cpp runs this cycle, this run method, which basically um, uh, runs the cycle method for every component of the simulator. So for every memory controller, for the memory controller, for the collection bus, the reduction network, the multiplier network, the distribution network, this file basically runs in a loop all the cycle functions of every component, so that everything works together, and all the information, all the data flow through the architecture, right? So that's how Stone is able to do this, to create this environment of cycle level simulation, right? So yeah, any questions so far, or otherwise we can start the hands-on. Any questions?
Should we continue? Okay, continue. Francisco.
Okay, so hands-on one. So how can Stone simulate a real DNN on a flexible accelerator, right? So the objectives of this hands-on is to understand how flexible architectures work, understand how to run simulation in Stone. That's, I would say, the most important thing, using the Stone user interface, and how to run Stone with the Pytorch framework, which I believe will be useful for researchers. So this is the benchmark that we will use during the presentation, during this hands-on. This is a very small real-life example to motivate the use case. And this is basically an application task, an image digit recognition application task, right? Where we will feed a CNN, a convolutional neural network, with a image which contains a number. And then the goal, the objective of this CNN will be to predict which number is written into the image, right? So that's the main picture. The benchmark, yeah, is a CNN, and the data set that we will be using is MNIST, which is a 60,000 image data set of, the size of the image is 28 cross 28, basically. And this is a very well-known data set. I don't know if um, anyone in the room is aware of it, but it's very, very famous in the community, right? So this is the CNN model that we will be using during this hands-on. We will be simulating, and we will be looking at. And here are the parameters that we have, right? So as you can see, there are 5 layers, right? We have a first convolutional layer, followed by a max pooling, another convolutional max pooling, and then a dense layer, which is a typical fully connected layer. And these are the parameters of each layer, right? I think Jose Luis has gotten into details about what do they mean, but if anyone doesn't remember, I will cover them. So R is, as you know, right? A convolutional network basically is a set of like input features, right? And then you have like a set of filters as well, and you get an output which has like different output features as well. So R is the size of the filter row, S the size of the column row, I mean the column filter, sorry. C is the number of channels in the filters as well as the number of channels in the input feature maps. Okay, K is the number of filters that we have, so it's the number of output features maps that we have as well. G is the number of groups, N is the batch size, which is the number of images that we are calculating at the same time, that we are predicting at the same time. X is your feature maps input size, in this case number of rows, and Y number of columns, right? So that is essentially the parameters we have. In the fully connected layer, C is the number of input neurons, K is the number of output neurons, and N, by the way, which is not highlighted here, but it should be, N is the number of batch as well, or batch size. So yeah, any questions regarding dimensions? I would say this is quite important for the rest of the hands-on. Okay, I assume no questions. So our stone simulator is able to simulate uh, matrix multiplication layers, we can say. And these are basically convolutionals and dense. Actually, the simulator currently supports also SPM operation, sparse matrix multiplication operations, and some more, but max pooling is not supported currently by the simulator. So we'll be simulating only convolutionals and dense in our example, and the max pool operations will be computed by the CPU, right? So this is what we will do. And we will be simulating our benchmark in a 64 multiplier Mairi architecture. This is similar to what Jose Luis has mentioned. This is a Mairi architecture. We have the distribution network, we have the reduction networks, and we have essentially in this use case 64 multipliers, 64 of these boxes, right? And then we have the memory controller, which is used by the simulator to feed data, to get the data from the memory and fit it into the simulator and all of this, right? And then we will have a distribution bandwidth of 64 and a reduction in bandwidth of 64. Distribution bandwidth means the number of elements that the memory controller will deliver at the same time. So 64 means that the memory controller and the network here and the distribution network is able to fit the accelerator with 64 elements at the same time. And reduction bandwidth of 64 means that we can reduce up to 64 elements at the same time. Okay, so we have fully bandwidth scenario here. Okay, so the question is, given our DNN, our layers with these parameters, and given this architecture with this number of multipliers, how can we map the DNN, or how can we map each layer, okay, which is composed of a million of operations? How can we map those operations on this architecture? Well, the answer is tiling the layer, okay? As Jose Luis has mentioned, we have to divide the layer into several tiles. And how do we do it, and how does Stone do it? Well, imagine this layer, right? We have number of R, which is number of rows in the filter, 2. Number of columns of the filter, 2, right? So we have square 2 size filters here. We have 3 channels, right? You can see 1, 2, 3, and 3 channels in the input feature map, right? Three images we can see here. And then we have k equals to 2, which means we have 2 filters, right? G equals to 1. G is the number of groups. I will not get into details. This is for some more complicated convolutional layers. I'm not going to get into this, okay? N is the number of batch, which means the number of images that we will predict, in this case 1. These 3 channels can be, for example, the 3 colors of an image. So we have only 1 image, right? Being predicted at the same time. X is 4, which is the number of rows in the input, you can see. Y is 4 as well, we have 4 columns. And then how many output rows do we have? 3, right? Because if you put the filters into the inputs and you slide the filter, basically doing sliding the convolutional window, you get 3 columns here, and the same for the number of rows. So we have 3 cross 3 outputs here, and we have 2 output channels, right? Because we have 2 filters, right? I assume you have some knowledge of how this works actually, even though I'm trying to explain it. So the question is how do we map? We have we have how many rows, filter rows, we map at the same time in the architecture, how many columns we map at the same time, how many channels, how many filters will be mapped into the architecture at the same time, groups, batch, X and Y, right? And how many elements, output rows we are computing at the same time, and how many output columns. So this basically means how many elements are we computing at the same time. Once one of these dimensions finish, for example, if we map 2 filters at the same time, once these 2 filters are done, we will be computing the next 2. And the memory controller will take care of all these parameters. So the memory controller knows how many tiles there are mapped, and how many loops it has to do to fit all the data, right, in the proper order. So that's the main goal of the memory controller, right? So how can we map this layer? How can we? What are the values here? So one option is this, for example, right? Which is okay. Let's map a whole filter here. So the whole filter will be like allocated to the architecture, and then every time we will be computing one output, right? So we will be computing this output, then the next k, the next output channel, and then we will go through all the output elements here. So that's the meaning of these parameters, right? And another option, for example, is okay here. What is the virtual neuron size here, right? I think Jose Luis has mentioned this concept. Virtual neuron is uh, a cluster of multipliers that work together to perform to calculate an output, basically, right? So what is the virtual neuron size? It's basically uh, TR by TS by TC, right? Because that's the filter size here, right? So we have a virtual neuron size of 12, and we don't have more virtual neurons because we are computing only one output element at the same time, because our TX and TY and TN and TG are 1, right? But what happens if we map at the same time only one filter channel? Well, we have space to map actually 2 channels at the same time, right? But if we map two channels from different filters, we will be computing two outputs at the same time, right? So this means, what is our virtual neuron size? Okay, we are mapping two filter rows, two filter columns, and one channel. So our virtual neuron size, our cluster size is 4. But how many virtual neurons do we have now? We are computing two outputs at the same time because we have two filters, and every filter computes one output, right? According to CNN's rules, CNN's computation. So in this case, we have two or TK virtual neurons, right? And the last case, we could map actually 4. We could map 4 clusters here. We could map only one filter channel, you can see, so TR equal to 2, TS equals to 2, but TC equals to 1, and TK equals to 1. We are computing only one filter at the same time. So only one output channel is being calculated at the same time. But how many outputs out of this channel we are computing in parallel? Well, that depends on TX and TY now. So we are computing two output rows and two output columns here at the same time, right? Because our TX and TY equals to 2. So how many clusters do we have? TX cross TY, because we are computing 4 outputs at the same time. And each output has size 4, right? So spatially, we are computing 4 outputs, but temporarily, we will map the whole filter 4 by 4. So that's the main idea, right, of how STONNE performs the tiling. And what about fully connected layers? Here we have 4 input neurons, and we are going to calculate 2 output neurons, right? The calculation of each output neuron is the accumulation of the of all the input neurons, basically, right? I'm assuming you have some knowledge on DNN computation. So how do we map the operations here? How do we map the 2 outputs? Well, we can do this. We can map actually the 2 outputs. We have enough multipliers, right? So here our TS is 4, basically, because we map the whole computation of one output at the same time. So TS is 4. We are mapping everything at the same time. And TK is 2. We are mapping the 2 output at the same time in a different cluster, right? So every cluster will perform the 2 outputs. I mean, every cluster will perform one output at the same time, right? So our virtual neuron size will be 4, or TS. And our number of virtual neurons will be 2, because we have 2 outputs at the same time. And if we had more input batches, which means a larger N and a larger Tn, we could be computing 2 images at the same time, or 2. It doesn't have to be an image. It can be any input, right? But several batches at the same time could be running, right? So that's how convolutional and fully connected layers can be mapped onto the accelerator, onto our 64 multiplier accelerator, right? So let's get back to our example. We have these 3 layers that we will compute. Layer 0, layer 2, layer 4. And we want to map each layer onto the accelerator. So we will map one layer, we will run that layer, then we will map the next layer, and then we will run that layer. So that's how STONNE works, right? The simulation is layer by layer, basically. Okay, so how can we do this mapping? So here we can see we have the 5 layers that we will run, right? and the 3 layers actually that will be simulated. And here we have how are we tiling them, right? So I'm not going to get into details, but the first layer will tile like this. Basically, we are trying to maximize the number of multipliers. We have 64 multipliers. We know we just basically manually are uh, trying to see what is the best tiling for that layer. So in this case is 5 by 5 and here 2 filters at the same time. The second layer is like this. Yes, we have 16 channels and 4K here. So we are mapping 64 multipliers, right? And in the fully connected case, we map spatially 32 inputs at the same time, and every 32 inputs will calculate one output. One will have 2 outputs, right? So this is how the whole picture looks like. We have our layer, our TNN with these 5 layers. 3 out of these 5 will be simulated, and these 3 will be simulated with these tiling parameters. And we are going to run this scenario into our 64 multiplier fully bandwidth accelerator, Mary accelerator. Okay, any questions so far?
Any questions? No.
Okay, so let's get started. How can we run STONNE? So the first thing, the first part is the STONNE user interface. So sometimes, right, we are I don't know, we are working with the simulator. We want to test out how a specific layer will perform. For example, imagine we don't care about, I don't know, about the real data that is being computed. We just want to check how long how many cycles does my architecture take to compute a layer with these parameters, with r equals to 5, s equals to 5, c equals to 1, k equals to 16, and you want to do it fast. You just want to type some parameters into the simulator and run this very small simulation and test it out how it works. Or imagine you are working with your simulator, you have done some change in the backend of the simulator, you have changed some architectural thing in your in STONNE, and you want to make sure that everything works fine. How can we do that? That is done with the STONNE user interface, which enables this way of using the simulator in a very easy way. And how does this STONNE user interface work? Well, that's very easy. So if you go to the root of the Docker, okay, and you go to a STONNE folder, and then again to STONNE, you will find here the stonne.elf file, the STONNE executable, right? So you can use this to run your parameters. For example, I want a convolutional layer. I want all these parameters. R equals to blah, 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 right? Here I actually have an example. Let me copy and paste because it will be faster. So I'm copying this. Okay, so here in comments underscore example.sh, you have some examples if you want to start using STONNE. Okay,
Francisco,
so
una-
yes.
one thing, please. Can you clear the screen so you can, type all the commands just at the beginning of the, on top of the terminal? That is now you have at the bottom you are typing, so it's better if you type clear, and then you can start,
Okay, I know what you mean.
it's
Yes.
better for the audience.
Okay, like this.
Yeah.
Okay, so let's run actually the first layer here. The first layer, r equals to 5, s equals to 5. Let's see how many cycles does it take. So I have copied pasted this command, right, which indicates to STONNE that this is a convolutional layer, and then we have to tell the simulator our parameters. So r equals to 5, s equals to 5, C equals to 1. Okay, I'm switching uh, to the slides. I hope it's not um, confusing. J equals to 1, right? K equals to 16, right? You see here. So K equals to 16. N equals to 1. You see here. X equals to 32, right? 32. And Y equals to 32. It is squared, actually. 32. Okay. Now, how are we tiling this computation? This is here, right? The layer 0 is tiled like this. So we will map 5 filter rows at the same time. So TR equals to 5. TS equals to 5. TC equals to 1. TK equals to 2, which means we are mapping 2 filters at the same time. Tn equals to 1, and actually the rest of the parameters are equal to 1. And then let's tell the simulator how many multipliers we want to simulate. We want 64. This is correct. What is our distribution network? 64. What is our reduction network? Bandwidth, I mean, 64. Okay. And what is the accumulation buffer? Equals to 1. Accumulation buffer is essentially a component that is used to accumulate values at the top of the accelerator. I'm not going to get into details here, but this is done to support folding in a more efficient way. Okay. So let's enable it. I would suggest that you always that run a Stone, you can enable it. Actually, it is by default enabled, but I wanted to explicitly show to you uh, how this works. So let's enable it manually and let's run the command. So, okay, we have run Stone right now for the first time. We are getting 360 number of cycles in this simulation. And the simulator, as it prints out here, the simulator prints statistics regarding the simulation. And also here we can show a nice message saying test passed correctly in green, right? Why passed correctly? That means basically that the Stone user interface creates random data for this layer. Here we are specifying our layer size, right? Our layer dimensions. But what is the actual data? What are our weights? What are our input data? What is the output that is being generated? All of that is random. Okay, so the simulator before running the command is going to create the matrices with random data, and then it will compute the outputs with the simulator, and then it will run the algorithm with the CPU, calculating the same outputs, and then it will compare the outputs that the simulator has calculated and the output that the real algorithm that the CPU has computed. And then the Stone simulator, and then yeah, the simulator compares the values and matches if they are correct. If they are correct, that means that the simulator has been successfully completed, that the output of the hardware that is being simulated is correct, and everything works fine. If some of this value was different in the CPU to the value that to the simulator, that would mean that the simulator is performing incorrectly, that the hardware that is being generated, that the hardware that is being simulated is doing something wrong and is generating a wrong solution, right? So the simulator will detect this. This is very useful for anyone who wants to change the simulator, who wants to change the hardware of the simulator, to check that the changes are done correctly and that everything works after the change. Okay. So, okay, now that we have run the simulation, where is our result? Our result, the Stone simulator generates two files. This .txt file, which is a JSON file with all the statistics. The reason why this is a JSON file is that it's very easy to write a JSON script in JavaScript or whatever language, but it's easy to extract the information from here. So all the statistics are here, and also there is this file which contains, for every component that has been simulated, how many operations it has performed and how many times this operation has been carried out. So for example, for a wire, right? A wire in the distribution network, we have that the wire has been written 232 times. Okay? That the wire has been put to active this number of times, we can say. If we go, for example, to multi, let me, yeah, here. So for example, for every other, we can see here, for every FIFO as well, we can see how many pushes we have done and how many pops. And even for the memory, me this 1 second. Let me search. I cannot find. Sorry about that. Give me 1 second. No. Yeah, sorry. Global buffer. Yeah. So for the global buffer, for the memory, we have the number of reads to the memory and the number of writes, right? And the same for all the accumulators. How many times this accumulator has written a value, and has performed an addition, a sum, right? So for every component, we see every like action that this component can do, and how many actions has been done for every type action type, right? So this is the main idea. So we have two outputs, and basically this counter file is used mostly by the energy and area script, because if we know for every component how many operation has been performed and what is the consumption of each operation, we can easily calculate what is our energy consumption, for example, right? So that's the main goal of this counter file. And this is actually shown here. So once the simulator has finished and we have these two files, mostly the counter file, right? We can use, the simulator uses a energy table-based model to calculate the energy. And it uses a table-based model to also calculate to calculate the area as well. And how does it work? Well, here in STONNE, okay, folder, we have energy tables folder. And in this folder, there are two files. One is calculate_energy.py, which is a script that automatically takes care of everything and calculates the energy consumption for every simulation. And then we have the energy model.txt, which is the table that can be used to calculate the consumptions. So just running this command, calculate energy, specifying here the table file and the counter file, we can calculate the energy and the area. Let me show it to you on live. So we have already our counter file here, right? Which contains for every component how many times each operation has performed, right? So how can we use it to calculate the energy? Well, we go basically here to energy tables, okay? And if we run the script like this, we see in this helper message how to run the script. So let me actually show you this file as well. Energy table. This table has for every component of the architecture, for example, for a FIFO, the area of a FIFO is this one. And the static energy is, in this case, is put to 0 because I'm not, for some experiments, it's good not to count the FIFOs and just take the energy from the wires. But anyway, for example, for the other, we have this area. The consumption of the other in terms of static energy is this one. And this is the dynamic energy of performing a 2-1 operation, assume a 2-1 addition operation. This means adding 2 values, and 3-1 means adding 3 values. In this case, it's the same in this in the Mari architecture. So yeah, this is the dynamic consumption of performing one of these operations. So if we have 1,000 operations, we will have 1,000 times 0.111 energy consumption. In this case, this is microjoules, if I don't remember bad, and the area is in nanometers. So if we use the script, we just use, let me clear again, okay, and the script like this. Now we have the reference. So calculate energy. What is the table file that we will use? Our table is right here, energy model.txt. The table I just showed you with the energy and area of every component. And what is the counter file of our simulation? Well, that is here, right? Dot counters. Then we can actually say code file equal to blah blah blah. And this will generate a file called file.txt with all the energy and area statistics. But if we don't specify a name, okay, this command will generate in the previous path, I mean in the path where the counter file is, it will generate a new file with the same name to the counter file, but in this case ending into energy, adding the energy suffix to the name. And if we open this file, we can see the energy consumption of our simulation. Here we see the table that we have used to perform the simulation, and here we see the consumption of the simulation. So here we see the consumption of the reduction network, the consumption of the global buffer, or the memory, the distribution network, the multiplier network. Here we can see the total static energy, the total dynamic energy, the total area, okay, and the total energy finally, adding static plus dynamic. Okay, so it's very easy to write a script to imagine you run 10 simulations for 10 layers, and then it's very easy to run a script, to write a script to read all these 10 stat file, uh, run this command for every file, and calculate the energy for all the layers, and I don't know, and perform some statistics based on users' need. Okay, so that's the idea of how Stone can calculate energy, area, and cycles, etc., and statistics in general. Okay, so last but not least, right now I have shown you how to run Stone with the Stone user interface, and we have executed the first layer of our CNN. We could be executing the rest of the layers as well. Like, okay, I can modify these parameters, run the next layer, the third layer, and simulate the whole CNN using this interface. But imagine in some cases that we mind about the values that are being generated. For example, we do some skipping zeros performance optimization, or we run Sigma, or we do whatever data value optimization we want. If we do that, it is very valuable to run the real DNN, right? To run the real benchmark in our architecture, in our simulated architecture. So to do so, we have connected Pytorch to STONNE, and let's see how can we use this interface. So we have 4 files. If any of you go to the Docker, let's go to the root again, okay? And here we have tutorials folder, which is the one that we have cloned. And then here we have ASPLOS 23, and let's go to hands-on 1. Okay.
Francisco, can you type here? Actually, your commands are at the very bottom.
Yeah. Okay. Now. Okay. So now we have we have 4 files here. One is train DNN, which is used to train our CNN. We have evaluate DNN, which is used to evaluate the accuracy of the CNN, and DNN.py, which defines the CNN, and deployment.py, which is the final file which will be used to execute the CNN with a real image. Okay, so basically the train DNN here. Okay, I'm open the file. Can you see it clearly? It just okay. It basically defines. Okay, this is the number, the name of the weight file that the script will use. This is like some transform component, transform object to perform some normalization into the input files, okay, of our and east images. So here, all of this is used to download the data set, to perform some normalization into the data set, and this is the main loop of the training. So how many epochs we will use to train? Now it is set to 10. I will set it to 2 because I want it to be faster. Okay, and then this will run the training process. So if you have some knowledge about the training, this is basically, this runs the output. This runs the model, the CNN model for every input in the data set, in the training set, and then it will calculate the loss. It will use the loss to backpropagate the difference between the real and the calculated value, and then it will run the optimizer to change the value of the weight, and yeah, this is the main process, right, of the training. So we will be running 2 epochs now. Let's do it. Okay, let's run. Actually, you have to use Python 3 in the Docker, otherwise it will not work. Okay, we run the script. We will train the network. This should take like 1 minute, so no more. So these are the steps that we will perform. We will do run train DNN. This is what we are doing. Then after that, we will evaluate the accuracy of the DNN based on the weights that we have trained, and then we will run deployment.py using the CPU, and we will see that our model is really able to predict a number written into an image. So let's let this finish. This is now taking a bit longer because I guess I'm streaming. Okay, I have set it to 2 epochs, so it should take no more than a few seconds. Sorry about that. Let's give it a second. Should be finishing soon. Yeah. Okay. It has finished. 1 minute of training, but we have a very low loss, so should be a good accuracy. And to check that out, let's run the evaluate. Now we have generated the weights. We can see them here. Okay, so let's run the script that evaluates the accuracy of the network. Sorry, Python 3. This takes very short. Okay, we have a good accuracy. You can see almost 98% of accuracy. So almost all the new images should work, should be predicted fine. Sorry. So this is the DNN. This is Pytorch. And as you can see here, in our DNN, my DNN, we have our layers. We have our convolutional layers with the parameters that I have shown you in the table, right? We have 16 output channels, kernel size 5, etc. This is how Pytorch works. Then this is followed by a reload and then the max pooling operation. Okay. Next, we have another convolutional network. These are the parameters. This corresponds exactly with the values here. Okay, just don't want you to get lost. So, and this is followed again by the max pooling, which is here layer 3. And then we have the dense layer or the fully connected layer, which is called linear in Pytorch. And this is the size, 1568 inputs and 10 outputs. Okay, with the prediction. This is the prediction of each number, basically. And yeah, and the forward method just runs the layers one by one. Okay, and returns the output. And then the deployment.py is the script that, as you can see here, it just takes one image from the data set, and it runs the model here with this image. Okay, and it gets the output, and it shows the predicted output. Okay, the predicted digit, and it shows the real label, which means the real data, the real number that is in the image. Okay, so let's run with the CPU. Sorry, Python 3. Okay, we have a predicted digit 9, real digit 9. So this works, the DNN works in the CPU. But now we want to run this into an accelerator. So why not using STONNE to do so? Why not simulating this accelerator and get the stats of the simulation? So let's do that. And to do so, you have to go to the model. Okay. And then we just have to slightly change the model and change every layer to simulate it. So this is not a convolutional 2D anymore, but this is a simulated convolutional 2D. This is simulated as well, and this is a simulated linear. And we have tell the simulator what are the parameters of my simulation, of my accelerator as well. What accelerator do you want to simulate? So to do so, to every layer, every simulated layer, you have to give the simulator what is my configuration file. So that is done with another parameter, which is called path2arc file, equals to the name of the configuration file. Where is our configuration file? Oh, sorry. Well, if you go back to the root in a STONNE folder, you have here simulation files. Here you can copy one of them, for example, MIRI 128, okay, and paste it here. Oh, sorry, this is copy command. Let me clear okay. So now I have this file, this is a typical STONNE configuration file. So here we are saying that we are simulating 128 multipliers. No, We want 64 actually in this simulation. Our reduction network is this one, which is the one for MIRI. You can see all of them in the GitHub, okay, all the configuration parameters. Our accumulation buffer is enabled. We have fully bandwidth. Okay, and our memory controller is the one for MIRI. Okay, so we have everything set up. Let's actually change the name to the file because this is not MIRI 128, this is MIRI 64. Okay, this is just the name, but it's good to have it properly named. So yeah, now this is the name of our file. Let's fit our layer here. Okay, this is our layer. Now, what tile are we using to tile our computation? Well, that is done in another parameter, path to tile. And where are our tiles? Our tiles are in this folder, tile 64, layer 1, or layer 2, or layer 3. For layer 1, for example, we have all the tiling parameters. Let's see here. Okay. Can you see the screen?
Yeah.
Okay, I assume you see the terminal now? Okay, so okay, I made a very small mistake. This is not underscore. Sorry about that. Let me remove it here, remove it here as well. Actually, I have the solution as well. So yeah, now let's run it again. Let's see if everything works. First layer has gone well. It's a bit slow. Okay. So now you see the simulator has executed. The first layer has taken this number of cycles. The second one is the most computing like intensive, almost 40,000 number of cycles, and the last one is just 535 number of cycles. And as you can see here, the predicted digit is 5. This is the output of the simulator. Okay, so all the layers have been simulated correctly, because otherwise the predicted digit would be different, and the real digit is 5. Actually, we can run it again, and you will see again that the simulation has gone. The number of cycles is the same because here we are not simulating sparsity, and as you can see, the predicted digit is 8 and the real digit is 8, so it matches as well. It's not always the same number because the model extracts a different image every time, so we make sure that that there is no bias here. So this is how we can run actually a STONNE with Pytorch. And I just wanted to mention very briefly, because I'm being a bit long. Let me share this. Okay. So the new version of STONNE actually includes a mapper to auto-generate the best tile. This is thanks Adrián Fenola Navarro, who is a student at the University of Murcia. He helped me a lot on organizing this setup for today's tutorial. And he's also the developer of this way easier to use. So
I think your audio is cutting out a bit.
I think technically this is second last slide. So
Maybe we can ease the bandwidth.
we can use some time, we can use more because it's just a second last session. It's more than it's fine.
Still Francisco, maybe even start.
Oh, I just got it. So
Yeah. Does the mapper also look at the best order? What is the best order? How to parallel?
Yes.
So mRNA.
Yeah, sorry, I lost it again. Can you
also,
hear me?
Yeah, can you
Yes.
repeat your question to Francisco? Yeah.
Does the mapper also look at the loop nest ordering and other aspects of the map space aside from tiling?
I don't hear very good. The audio quality is not good enough.
Does the mapper also look at the loop ordering, or does it just look at the tile sizes?
Uh, the mapper looks at everything actually, tile sizes and loop order, but in this case, the loop order actually is the same in all the cases. I mean, Mary works with the same loop order actually. In this case, actually, only for SPM operation we have different loop orders, or only for Flexagon. I will show it. This is the second Hanson, but the mapper mostly takes care of tile sizes, not loop ordering, because it's always the same.
So yeah, so like the mapper for Mary, so since the architecture itself is running a fixed loop order.
Yeah. More questions? So what I was going to say very quickly, and we finish this part, is that if you want to avoid this difficulty of having to, where is the command? Anyway, it's here. Commands example. Okay. In order to avoid having to put TR, TS, TC, all the parameters and calculate them, this student has incorporated this nice STONNE mapper, which basically makes everything automatically. So it's very convenient. So if you just, rather than putting TS, TC, TK, you just type generate tile equals to energy. For example, let me copy this. Let me copy this command. Okay. So as you can see, let me clear. Okay. Now I don't have to specify the tiling parameters. The mapper will do it automatically and will try to maximize uh, multiplier utilization, and will try to um, maximize performance or minimize energy. So for example, if we run a simulation like this, the mapper automatically takes care of the tiling parameters. These are the tiling parameters that has been generated for this layer. So this is a very convenient way of running STONNE, and this really facilitates the usage of the tool. And this is also available for the Pytorch interface. So for the Pytorch interface, you don't need anymore to specify a different file for a different layer. In this case, you just have to create a file which indicates your layer type, and it will say, okay, generate tile, in this case maximizing performance, and then the layer will run automatically without having to specify the tile. Okay, so that is all for now. Now I think we have a coffee break.
So
Please, I would actually kindly ask everyone to be like on time. And yeah, we can continue after 15 or 20 minutes.
Francisco, actually, right now is 4:13, so we have skipped the coffee break because also we have started off the tutorial 20 minutes later. So we are not going to have a coffee break because he has passed already. Now,
Okay.
yeah, now is 4:10. So actually 4:10 is the starting the Omega part. So what I suggest is
Okay.
just introduce SST STONNE, so just to give the general idea about how you have integrated both tools, And just give an example, since we are going to just share the slides with all of you, we can
Okay.
provide some offline discussion so we can finalize the tutorial on time. Okay, Francisco?
Okay, let me be very quick. Yeah, thank you. So this is the second hands-on, how to simulate Flexagon using SST Stone. So first of all, what is SST Stone? So Stone simulator itself, okay, the simulations that we have just executed, they don't model a proper memory hierarchy. They don't model a proper, they only model the data path, and the memory hierarchy is just a global buffer structure with latency, with access latency 1 cycle, and it's not really modeled. Okay, so this is a screenshot of the code. So as you can see here, when you want to fetch some data into the simulator, the code only goes to an array of data, and it access to the proper address in the array, and it fetches the data automatically. So there is no latency, there is nothing, right? So there's no proper memory hierarchy, I insist. So the goal of connecting, yes.
Francisco, can you click on presentation mode? Because we are not, it's very tiny, you know.
Yes, sorry.
Yeah, no problem.
Let me very quick. Sorry about that. Okay, we are here. Now you can see, right?
Thanks.
Okay, so as I was saying, here memory hierarchy is not modeled in the version of Stone I just showed you. So for that reason, we integrated Stone into SST simulator, creating SST. So SST basically is a simulator from Sandia Labs, and is an environment, a structural simulation toolkit, is a whole environment to include more simulators. So we could have, in this SST simulator, we could have a simulator for CPUs, we could have a simulator for GPUs, we have a simulator for GNNs, we could have a MAERI being simulated here, and we could have a simulator modeling mem hierarchy. Then SST defines how these simulators interact between each other and how they send data between each other. So we have incorporated in Stone into this structure, this environment. So Stone now is able to connect to mem hierarchy, which is a simulator inside SST. So Stone inside SST sends packets of read and write requests to mem hierarchy simulator, and then this other simulator, which is done by Sandia Labs, takes care of modeling the memory hierarchy, and then the responses reach Stone back, and then Stone continues the simulation. So it's a mix between Stone and mem hierarchy simulator inside the platform SST. For further information about SST, just go to their website and you can check it out, and how it works and how to install SST Stone. I'm not getting into details here, okay? So here this is the link to the repo SST elements with Stone, okay? But everything is in the Docker. SST is a bit hard to install sometimes, and it could be problematic with the versions with SST Stone. So I would highly recommend to use the Docker that we are providing here. Okay, so yeah, this is the project organization. I will be very quick. Yeah, I'm not going into details here actually. So the idea is that in this implementation of the mem hierarchy, uh, different to legacy Stone. In this case, when we have a data address, in this case we perform do load operation, and this operation sends the packets to the mem hierarchy simulator. So this is the piece of the code that sends the packets to the SST simulator. Okay, and actually, yeah, SST Stone can be found here. So if we go to the root of the Docker, here we have SST Stone, and then in SRC we have the code. we can go to SST core, which is SST environment, and we can go to SST elements with STONNE. And here we have basically everything related to SST elements. So every simulator in SST is an element. And one of these elements now is, let me go to elements here, yeah, is SST STONNE. So here you have the code of SST STONNE. You have here STONNE linker SRC. This is the code that links STONNE to mem hierarchy simulator. Okay, I'm not going to get into details. And here is the source code of STONNE. And in this case, we have modified the memory controller to send the data to the memory hierarchy simulator. Okay, so that's the main idea. And this is the main file that incorporates STONNE into SST STONNE.cc. Okay, so this scenario allows us to model more accelerators or and to model sparsity accelerators, because right now we are able to from this point we are able to simulate like real use cases, real sparsity accelerators. We are able to find patterns in the memory addresses to really we are able to perform research on the whole like accelerator scenario, right? So for this reason, SST STONNE is very accurate when it comes to simulating sparse DNNs, sparse accelerators, sorry. So what is this? Sparsity matrix is basically, as you know, is an emerging trend in modern DNN workflows, right? So the thing is that the main operation in these sparse DNNs is the SPM operation. So every sparse layer is basically transformed into this operation SPM, which is a normal matrix multiplication, but in a sparse mode, encoded in a CSR and or CSC format, right? So two encoded matrices are used to calculate an output encoded matrix. And there are several ways of performing this multiplication, or what we used to call what we typically call in the research area data flows, which is how the loop orders perform to perform the multiplication. So we have inner product, outer product, or Gustafsson. I'm not going to get into details. This is basically based on the loop orders how the calculations are done, right? Actually, there are not 3 but 6 type of data flows. Yes, all the loop order combinations, and based on this you have a different memory access patterns and you have a different performance. And yeah, this is basically what we have observed in our research, and is that normally there are layers that benefit from a different data flow or other, right? There are layers that obtain more performance with some layers, and layers that obtain more performance with other data flows. So the idea is there is heterogeneity when it comes to the best data flow for each layer. So current accelerators nowadays are only implement one data flow, and this is suboptimal, because if the accelerators cannot adapt to the different data flows, um, the accelerator will always get like less performance, because they will not be able to switch. Okay, so for this reason we came up with this idea of Flexagon, which is a new accelerator able to support the 3 data flows: inner product, outer product, and Gustafsson. Actually, Flexagon supports the 6 variants: inner product M with the M loop in the most outer loop order, or inner product N, outer product M and N, Gustafsson's M and N. I'm not going to get into details. Flexagon will be presented actually on ASPLOS 2023 on Tuesday at session 4C. If I was there, I would be taking care of this presentation, but since this is not the case, I think Jose Luis will be there explaining the details of Flexagon. So the thing is that evaluating Flexagon requires a good model of the memory hierarchy, because we really need to model the memory access patterns of each data flow, right? Which is the critical part here. So for this reason, Flexagon is implemented in SST STONNE, and this is the way the results are obtained in our Flexagon paper. And this is done by implementing in SST STONNE 3 memory controllers, one for each data flow, inner product, other product Gustafsson, and a new reduction merging network that will be presented in our Flexagon session. Okay, so as you can see here in the code, if you go to SRC, you will find 3 memory controllers. Outer loop SPM, okay, which is the one for outer product. Gustafsson's is in Gustafsson SPPM. Okay, so we have one file for every modeling a memory controller for a different data flow. And finally, sparse, it's a very weird name, but this is the name for the MRN, okay, for our merging reduction network. So let's run Flexagon actually. See can how we can execute Flexagon on the how can we run a particular like SPM operation using the 3 data flows in Flexagon. So to do that, let's go to the root of the Docker, and I will finish. Okay, so I'm at the root of the Docker. Now SST STONNE. No, sorry about that. I'm trying to be quick. And okay, so I'm at the root of the Docker. I will go now to tutorials. This is in our tutorial repository that we have cloned. And then I will go to ASPLOS 23, and I will go to hands-on 2. Okay, and here you have an example of Flexagon. You go to Flexagon example, AlexNet. This is basically what we are going to simulate is SPM operation for AlexNet, for the 3rd layer of AlexNet. Okay, so if you go here, you will find 3 main folders: Gustafsson's M, inner product M, and outer product M. This is the 3 folders which contain the scripts to run SST for each data flow for the same layer. So if we go to inner product, you will find here all the scripts. First, you will find here ACC bitmap.in. Here is actually like how the data will be, the matrix A will be encoded. The same for matrix B. Here, this is the memory that will be loaded into the mem hierarchy simulator. This is our data. And then we have here the architecture that we will simulate. As we can see, we have sigma here because this is an inner product, and we are simulating 64 multipliers. And this is the script for SST STONNE. This is a typical SST script. I'm not going to get into a lot of details, but here basically you define a component STONNE, okay, and then here you say, okay, this is my hardware configuration, and this is the file that I just showed you with the configuration parameters. Then you have, okay, this is the kernel operation, which is SPM. These are the SPM dimensions. Okay, so k equals to blah, 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 n equals to 121, and m equals to 256. So these are the matrix multiplication dimensions, basically, right? And here you have like where is in DRAM my matrix A, where is in DRAM my matrix B, and where is in DRAM my matrix C. And here you have, okay, the statistics for the memory will be located in this file. I mean, the results of the computation will be in this file. Okay, so you can check that everything works fine. And then you have to define another component, which is the memory hierarchy simulator. And here we define the level of the memory hierarchy that we want, then the number of cache levels that we want. For example, here we are defining an L1 cache. Okay, here you can specify your cache accesses, the frequency of your cache, the coherence protocol, everything regarding the cache, the size as well, which is important here. It's 2K, 2 megabytes cache size. And here there is another component which is using also the memory hierarchy simulator, but here we are simulating the memory, the main memory, okay, the DRAM basically. And this is the access time, and this is the size, which is set now to max address 16 gigabytes. Okay, so here you can play out with your parameters and specify any cache access latencies. You can set more cache levels. You can change your latencies in DRAM, anything that you want. Even SSD can be used with DRAM SIM. So if you are used to using DRAM SIM, you can connect this to DRAM SIM as well. Right now we are just using the DRAM that is modeled by MEM hierarchy simulator by default. Okay, so to run the simulation, you just have to run SST STONNE inner product. This actually takes a bit of time, and even more now because we are streaming. So I'm not simulating it, I'm not finishing, but the results actually are here. So this is actually what you expect from running the command. You will find your txt file, the JSON files, the output of STONNE, your counters file. Okay, here all the number of cycles that you have here is counting also the latencies regarding the memory hierarchy. So everything is simulated correctly and accurately. Okay, and then you have also this extra stats file, which is I mean, this is the output of your computation, and this is the .csv. Yeah, this is the statistics of your memory hierarchy. And this actually, for further information, I would refer you to the MEM hierarchy simulator actually in SST. But here you can find the number of accesses to L1 cache, the number of misses, the number of hits, and all of these statistics can be found here. Again, I don't want to get into a lot of details here. Okay, so this is how we can run in a product. And just to finalize, to run, for example, other product, you just go to other product. Everything is ready. Oops, sorry, not here. To AlexNet layer 3. Let me clean outer product. And then here there is the STONNE configuration file. As you can see here, we are using outer product controller, memory controller. And here we are simulating the number of 64 multipliers, and we are using our merger, our MRN network, right? And here is the SST script. Again, the same parameters, but in this case we used the STONNE outer product version, right? The configuration file. So we can run it in the same way, just doing SST STONNE outer product. Okay, and the same for Gustafson's. So yeah, if anyone wants to run SST STONNE, you need your call pointer, row pointer files, which contains the matrix row pointers. For this, you have to know the CSR CSC format, which has basically a row pointer, vector, column pointer. So all of that is indicated here in this file. This is the row pointer. This is the for A. This is the row pointer for B, call pointer for B as well. The same for A. Here, the memory with the data. Okay, this will be loaded into the DRAM. And then if you want to run any layer, you just have to extract this data, extract the data here, prepare it in a good way. You can find tests in SST Stone Simulator. You can find more like scripts to generate these values. But once you have the values ready, you just have to prepare your SST script like this, and run any simulation at your taste. So yeah, I think I'm gonna finalize here because I don't want to extend more the tutorial. We are running late, and I don't know if you have any questions, something you want to share.
Questions? Okay.
Okay. So next, I think Ravish will proceed to explain Omega, which is another simulator working upon Stone. And actually, it's very late in here. I'm in European time, so probably I will drop off. But I'm really glad to have presented and to have you all there. So thank you, everyone.
Yeah. Yeah. Just a second. I need a minute to set up. I was about to do this during the break, but yeah, I think.
Thank you, Francisco. You can drop off then relate to right now. We appreciate that you are here with us. That's working late for us. So thank you.
Yeah, thank you, Jose Luis. Thank you, everyone, for coming, for attending. Okay, see you, guys. See you, everyone.
Um, Hi, so I'm Ravish and I'll be presenting the next part of the tutorial, which is understanding the design space of sparse dense. Oh, actually, let me turn on my camera. Sorry. Um, yeah. Sorry about that. Yeah, so I'll be presenting understanding the design space of sparse dense multi-phase data flows for mapping graph neural networks on spatial accelerators. Yeah. So this is like the fourth part of the tutorial. Yeah, so graph neural networks are becoming popular because a lot of the real world data is actually irregular rather than like the convolution data where you just have the spatial filter, which is in a very regular shape where you only have you have like a fixed X and Y coordinate of neighbors for each of the pixel of the image. But here, the data is quite irregular, and there can be arbitrary relations between the data, and graph is like one of the most popular data structures to capture this kind of an irregular data. And it's used in social networks, biochemistry, and in various other applications. Graph neural networks are basically learn from this irregular graph data. So we have this graph of various nodes. So the aggregation phase is the first phase of graph neural networks, which basically adds the feature maps from all the neighboring vertices. So for example, vertex 4 here, so vertex 4 basically adds the feature maps from vertex 3 and vertex 6. And then the combination phase is a feature transformation phase, which basically uses trained weights similar to deep neural networks. So it basically transforms this feature map to another feature map. So basically graphs can be represented as an adjacency matrix where the non-zeros represent the connection between the two nodes, for example here, and this effectually can be represented as SPMM, which is sparse times dense matrix multiplication operation, and the combination phase as a regular DNN is the feature transformation phase, which can be represented as a gem. So you have like the intermediate matrix here, and you have the weights, and you can just represent it as a general matrix multiplication. So basically your GNN layer is a sequence of SPMM and a gem phase. You have the aggregation and combination phase, and there is an interplay of sparse and dense computation. There are also several reuse opportunities between the two phases. And if we were to explore the design space of a GNN layer, now the design space practically squares because you have, So the design space now squares because now you have two matrix multiplications. Since there is a dependency between these phases, the design space further complicates. There are reuse opportunities between the two phases, but this makes the design space of data flows and mappings more complex. To this end, we basically propose a taxonomy to classify the graph neural network data flows, and we also propose our simulator, which is an extension of STONNE, which is called OMEGA, to model these GNN data flows. So just to recap, the intraphase data flows, they represent data flows within one phase. So for example, this is a matrix multiplication with the dimensions V, F, and G. You can basically have this loop nest, and the loop order of this loop nest is VGF, and you can select any loop order. So loop order is like one characteristic of the data flows, and the other parameter is the tile sizes. So that indicates the parallelism of these dimensions. And combining this, you can basically have a notation VS GSFT, where the order of the dimensions represents the loop order, and S represents spatial, where the tile size is greater than 1, and T represents temporal, where the tile size is equal to 1. And then now we come to the interface data flows. So it basically interface data flows defines how the data flows, how the reuse happens between the phases, and we classify them into 3 categories: sequential pipeline, and parallel pipeline. And I'll go into these in more detail now. So sequential data flow is your regular execution of DNN, which most of the accelerators do. So you have your full like matrix multiplication, P's like completely run aggregation. You do the whole matrix multiplication, write the whole result inside the whole memory hierarchy or the global buffer. You have to write this whole intermediate matrix inside this buffer. So the occupancy of this buffer is V times F. And then you have to read this matrix in order to do your next computation. You do the next phase, which is the combination phase. This is the regular sequential data flow where there is no reuse between the two layers. You just do the layer, write the complete intermediate matrix, and then read the complete intermediate matrix again. So coming to the sequential pipeline data flow or the SP data flow. So here what we do is we basically only do a part of the first phase. We only do a part of aggregation. So let's assume we split the computations row wise. So instead of doing like the whole A matrix, we only do some rows of the A matrix, and we basically write this part of the output inside the global buffer. The occupancy of the intermediate matrix inside the global buffer is tile V times F instead of V times F. So it is much less. So now what we can do is, so as you notice, the P's currently are doing aggregation. Now what we can do is we can, within the same P's, we can stream the weights onto those P's, and we can start doing the combination phase without doing the rest of the aggregation. So we use the intermediate matrix that we computed previously and do combination on that. So we are reading T underscore V times F data from the buffer. And then we move back to the second row. We do the aggregation for the second row. And then we do the combination for the second row. So we basically interleave the, we split aggregation and combination into multiple smaller parts, and we interleave the computation. The consequence of that is that the occupancy of the intermediate matrix inside the buffer is less. So we can use smaller memory hierarchies to store such intermediate matrices, or like at a very fine granularity, you can just do it within the register file of the P's. You don't even have to go to the global buffer. So this is one of the advantages of SP data flow. You are basically reusing the part of the value, the intermediate matrix that you had computed earlier, and you're doing the next phase on that. The parallel pipeline data flow or the PP data flow is similar to SP data flow, but it basically does the reuse spatially instead of temporally. So we divide the whole compute substrate into two parts. The first part does the aggregation phase, and the second part does the combination phase. So we do the aggregation. The left half does the aggregation for the first few rows, and then on the previously computed rows, we do the combination phase, which is represented in orange. And in parallel, we do the aggregation for the next row. So this is kind of like a pipeline manner where we are doing combination on the first row, but we are doing aggregation on the second row in parallel to that. So instead of reusing the data temporally, we reuse the data spatially. So the occupancy inside, at a given time, the occupancy of the intermediate matrix inside the buffer, the maximum occupancy would be 2 times T underscore V times F, because you need T underscore V F for T underscore V times F for each phase. And then you're already done with the first row. You don't need it anymore. You can just discard it from the buffer, and you have like the second and the third tile inside the buffer. So if we look at the data movement in sequential pipeline and parallel pipeline data flows, so in the sequential data flow, you have this whole data which has to be written into the buffer, and then it has to be read from the buffer. So this consumes a lot of energy because you're going into like the higher layers of the memory hierarchy, and DRAM accesses, of course, consume a lot of energy. Instead, if you could just write a part of the intermediate matrix, read it and finish it off, you are basically having less net occupancy inside the intermediate buffer. You can store them in lower layers of memory hierarchy, so you don't end up consuming a lot of energy. In parallel pipeline, similarly, instead of doing this reuse temporally, we are doing it spatially. So SP and PP data flows reduce the data movement of the intermediate matrix by consuming the part of the data right after producing. So there is an interdependence between the data flows. For example, if you were to split this whole thing row-wise, you produce the intermediate matrix in a row-wise fashion. You also have to consume it in a row-wise fashion. So if we, for example, if in this VF matrix, if we are doing V major order for the aggregation phase, we have to do V major order for the combination phase. So there is an interdependence between the data flow. So unlike the sequential data flow, you can't just do any data flow for the aggregation phase and any data flow for the combination phase. There is an interdependence, and the way you are producing determines how you would consume the data. So we have a lot of details in the paper. So actually, yeah, right now this is the link to the preprint, but this is actually a published paper. So I'll also include the IEEE link into the slides. But for more details, you can refer to the paper where we also tease out various interdependencies that can happen. And if there's a parallelism mismatch, how do we handle that by still ensuring that we are pipelining it efficiently. So yeah, SP and PP data flows are interdependent. So our taxonomy basically covers the type of the interface data flow and the intraphase data flow, and it also covers the phase order. Yeah, I'll not go into this in detail, but we do like a very detailed analysis of all these data flows, and we also highlight the previous GNN accelerators which have used these data flows. So like these are some data points on our taxonomy, basically. Yeah, so our taxonomy can accurately capture the data flows used by the state-of-the-art graph neural network accelerators. So some of the qualitative observations are that sequential, you can run any intraphase data flows. SP and PP are more constrained. Even within SP, if you want the intermediate matrix to remain in the register file, you should also make sure that the parallelism strategies match each other, because the data cannot go out of the register file. And then PP or the parallel pipeline data flow also requires consideration of load balancing between the phases, aggregation and the combination phases. So there are a lot of trade-offs. So on one hand, you have sequential, which is inefficient with respect to the interface data flows, but it can model, like you can do any data flow within aggregation and combination phase. While SP and PP data flows are more constrained, and you, although it's more efficient when you want to do operation reuse. So there are numerous trade-offs in these data flows, and therefore a detailed quantitative modeling of these phases is needed. So to this end, we propose the Omega cost model, which is an extension of STONNE. So the input to the cost model is the dimension of the graph neural network layers, and the data flows and the tile sizes, hardware parameters. So right now we do the number of P's, and we model the distribution and the reduction bandwidth. And since the graph is sparse, it is data dependent. So we need to supply the input graph in the CSR format. So Omega basically builds upon STONNE. So STONNE can model SPMM, GEM, SPM, SPM, and various kinds of kernels. So we model we run the whole simulation with an SPMM accelerator, collect all the timestamps, runtime, and the buffering statistics. We do the same with the GEM accelerator, and we collect all the timestamps, runtime, and buffering statistics. And then we phase it into the interface cost model, because if we were actually interleaving the computation, or we were doing the spatial pipeline of those computations, the interface model, a cost model, can intelligently model those data flows as well. Sequential is just simple. You just add the runtimes from both SPMM and GEM accelerator numbers, but our cost model can do interface data flows as well. And then we get the runtime energy and the buffering stats as the output. Here are some of the equations of that are interface cost models. So basically, we need like the runtimes and the buffer accesses are heavily dependent on what we obtain from individual layer simulation. So like the cycle accuracy for individual layer simulation is paramount. So yeah, now we'll switch to the hands-on. So in order to open Omega on the Docker, we just do yeah, so we do CD Omega. So sorry, yeah. So if you go to the root and you can do CD capital Omega, you'll come to the Omega directory. Yeah, this is a bit. Yes. Yeah. So basically, in order to compile this, you can just do make Omega. I think the clear is okay. Oh, good. Oh, sorry. We have to do CD Omega under Omega dash code. And then make Omega. Yeah. So I had already built that, so it's up to date. Yeah. So if we do, if we look at the Omega directory, we have like a few files. So sample. So if we go into sample underscore graphs, and we do ls. So we have vertex underscore dataset and we have edge underscore dataset. So edge basically is the represents the coordinates of the CSR, and vertex represents the position data of the CSR. So CSR has like three kinds of metadata: value, which is here always assumed to be 1, and the position and the coordinate. So position is represented by vertex underscore dataset dot txt, and the coordinate is represented by edge underscore dataset dot txt. So this is the these are the sample graphs, and we can also go through the code. I'll just be brief. So if we go to STONNE SRC, so all this information is also there in the slide, so, and in the recording. So yeah, so if we go here, so the first part is basically config parameters. So all we are doing is we are basically, right, this is the code to add, like you can modify this section of the code to add any new command line parameter if you're interested. Then basically the next step would be to read the MK matrix, which is like this sparse matrix, because it is data dependent. So you have to read like the position and the coordinate values. So this is what the next section of the code is doing. And then the next section of the code basically defines, the next section of the code basically defines an instance of STONE. So the first instance is basically running SPMM, and then the second instance is running the dense gem. And then the third part of the code is the analytical model. So all the timestamps that we have collected from the SPMM and the gem, we just use analytical modeling in order to get the get SP and PP data flow numbers. So so this is like the brief summary of the wrapper of the code that I have. And now we can go to the exact simulation. So so there's a file example_simulation.sh. So we can see that. So omega./omega is basically the binary, and you have vertex feature, input feature, output feature, and you have edges. And then you have tile size of vertex for aggregation phase, tile size of reduction of neighbors in the aggregation phase, and then the feature map in the aggregation phase. And you have okay, this is covering this thing. Let me actually switch to the slides for this one. So and you have various tile sizes, and you have the number of P's in the aggregation phase, number of P's in the combination phase. For PP data flow, of course, like it will return the result with double the number of P's compared to like the SP and the sequential data flow. So for apples to apples comparison, we generally half the number when we are running PP data flow. And then there's path to the vertex, and then path to the edge. And there is like this is like a legend for parameter translation from STONE to OMEGA. And as I just briefly went through the OMEGA code. So you pass the command line parameters, read the matrices, instantiate and run STONE for SPMM and GEM, and then there are interface analytical equations. And then we can run an example simulation. So we just source example simulation.sh. Some of the things I was just, so if you want, you can also like print the timestamps. Basically, once you're done simulating, so you can see separate statistics for the simulated SPMM, where you can see the register file weight reads, register file input reads, and register file partial sum reads and writes. And you can also see the global buffer statistics, and then you can see like the same individual buffer statistics for simulated GEM operation, and then you can see like the overall statistics for each of the interface data flow. So this is PP data flow parallel pipeline, and then you can see it for sequential data flow, and then you can also see it for the SP sequential pipeline data flow. And then you can see all the global buffer statistics separately for SP, PP, and sequential data flows. So this is what the output file looks like. I've also included the screenshots and in the slides. So I mean, this is just like for changing some of the parameters, and I won't go into this in the interest of time, but we can just edit the example simulation file, or we can copy and create a new example simulation file, and we can just edit the parameters that we want within this, and we can simulate it again. So basically several important workloads in ML and HPC have multiple phases, and it is crucial to consider like the pipeline data flows which can exploit reuse between these phases. So we capture this data flow using a succinct taxonomy. So prior works on data flows have mostly focused on data flows for one layer. So we propose taxonomy to capture the data flows for multiple layers, and we propose an analytical model to model such data flows. Yeah. So I'll hand over to Tushar for the roadmap.
Yeah, thank you for the time. I'll just keep this very brief. Thank you all. Let me actually just. So we're basically here. I'm actually gonna jump to and just go talk about some very important pieces. One is, the link, of course, to the simulator. Please check it out. I want to kind of go over some key things about like next steps, right? So we would love to, I mean, this is an open source project. We would love to have your contributions. So if you have any, bug fixes, like please create like pull requests and so on at the link here. This includes both the main simulator, the SST plugin, or Omega, right? And we would love to hear from you. So of course you can, feel free to reach out to Jose Luis, Ravish, Manuel, myself, Francisco. Francisco is like graduated, so I don't know how much bandwidth he'll have to respond, but please feel free to reach out to us. Or of course, this is another email ID we'll be monitoring. You can reach out to us on this as well. In general, of course, we are looking at further efforts for both STONNE and OMEGA to work with other frameworks and some additional enhancements as well. And, as kind of we go forward, we're going to start releasing those updates as well and update the readmes. So again, thank you all for coming. And this entire tutorial was recorded, so we will actually upload the recording and please feel free to share it with other colleagues who might be interested in this infrastructure as well. And again, one shout out, the fact that, we have a paper on Tuesday called Flexagon that Francisco actually talked about. So please, looking forward to seeing you in that session as well. Thank you all, and we'll officially close the tutorial. Yeah, you can turn off. Yes, and just stop the recording as well.
Just click on stop. Yes.